Let's begin our review of the June 2023 Regents Chemistry exam. Under the description, there is a link to the time code to every single question. So if you just want to move to a certain question, please look under the description to do so. If not, want to stay along for the entire ride, let's go. So let's be crazy and start in order with number one. So number one. Which phrase describes the nucleus of the atom? Okay, well, this is really important that you should know the basics of the atom at this point, but Ernest Rutherford had a very famous gold foil experiment. And what he did is he actually discovered the nucleus of the atom. He shot alpha particles, which we should now know, okay, are helium nuclei, and he saw that most of them went right through. And the reasoning is very simple. Most of the atom is empty space. Occasionally, these nuclei of helium atoms called alpha particles deflected, very occasionally. And why would that be? Well, they got close to that atomic nucleus. He discovered the atomic nucleus. And the atomic nucleus is a small part of the overall atom, but it's positive. That's why they deflected. Positive helium nuclei, of course, their nuclei also, they're positive. So positives and positives repel. You should know that the nucleus has an overall positive charge. Ernest Rutherford in the gold foil experiment discovered that because he shot positive particles and they what? Deflected away from the positive nucleus. So when you shoot a positive toward a positive, they will repel themselves and deflect away. So it's very important. Now, we also discovered later on that in this nucleus, where the entire mass of the nucleus exists, there was also neutrons. Okay, so the entire mass of the atom is due to protons and neutrons. Now, as the word describes neutrons, they don't have a charge. So again, if we look very carefully, and again, I'm over teaching this so you completely understand this, helium has an atomic number of 2 and a mass number of 4. This atomic number of 2 means 2 protons, which are both +1. And of course, there's a mass of 4, which means what? Well, there are 2 other particles in the nucleus that have the same mass as a proton, and that would be a neutron. And that's what an alpha particle is, 2 protons and 2 neutrons. It's a helium nucleus. But the entire, nucleus is a +2 charge in this case. We call that a nuclear charge. So these are kind of things that you should know as I'm going over the background. So obviously, which phrase describes the nucleus of an atom? It has an overall positive charge because the other particle in the nucleus that has the same mass, the neutron, has no charge. Okay, so that's why number 1 is your answer. All right, moving on to number 2. So number 2, which of the 2 particles each have a mass approximately 1 atomic mass unit? Now, 1 atomic mass unit sometimes is written as AMU, or it's written as just U. It's a relative scale. You can't put, a proton, neutrons, or electrons, or positrons, whatever these choices are, on a regular scale. So just understand that those are just units made up to measure the relative amount of these tiny, tiny particles. But they're basically saying in this question, which 2 particles, have about the same mass? And if you didn't see number 1, we understood that protons and neutrons do. Now, I can just tell you that, but you can also go somewhere to remind yourself. So if you go to table O, and a lot of teachers don't utilize this table for atomic structure. They just use it for nuclear chemistry. Let's go to table O, and I'll show you how you could have reminded yourself about that. Now, it's written table O, but I kind of like the Brooklyn feel. Table O! Okay, so table O is what we're going to call it here. All right. Yeah, if you don't know, table O is your friend. And notice we have this alpha particle with Ernest Rutherford shot. It's a helium nucleus. And what you should know is that the top number is the mass number. So if you get up close and personal with this is the mass number of the particle, and this is the charge of the particle in table O. Okay, now, if we look at the bottom, or toward the bottom, we have a neutron with a mass of 1 and a proton with a mass of 1. Notice they have an H there because H is the atom that only has 1 proton. So that's why they have a nucleus of what? Of a hydrogen is a proton, because a proton has 1 proton and has an electron, but just a nucleus of hydrogen is just a single proton. That's why it's there. But the bottom line is, what I'm trying to show you, my friends, in chemistry, is that they both have 1 mass unit. So protons and neutrons have approximately the same mass. Notice that a positron, as we saw in the choice, is given a 0. Okay, then that's not 100% accurate. It's very, very small. It's about 2,000 times smaller than that of a proton and neutron. So we give it a 0 because when you compare it to a proton and neutron, it just doesn't have enough mass to be significant. A beta particle, by the way, is another word for an electron. And if you notice, for an electron, although not in the choice, it's given a 0 too, but we know it's also about 2,000 times lighter. Notice its charge is what? -1 for an electron. Notice the E there. So some nice things given out here in table what? Table O. Okay, so let's go back. So clearly table O can remind you that the proton and neutron both have the same mass. Okay, and of course you should know they're located in the nucleus. Everything outside the nucleus is that empty space. I'm trying to reinforce these important concepts. So let's go back to the test. All right, so which 2 particles have the same mass? Table O tells us a neutron and a proton. So number 3 is our answer. Moving on to number 3. So number 3 states the wave mechanical model of the atom describes the location of electrons. Okay, the wave mechanical model is the current model of the atom. It's what we're currently using. So this is really important that you understand how the model of the atom kind of developed over time. We knew, or there was evidence that John Dalton that utilized either from his own experiment or other experiments that there were tiny little particles that were responsible for pressure. And so if these little particles hit your hand, they make pressure, or they hit your hair, they make the hair go back. So they thought the particles were solid spheres initially. J.J. Thomson discovered that, wait a minute, there's these negatively charged particles in the cathode ray experiment. It's called the plum pudding model. These electrons were haphazardly placed, okay? And so when we go to the next model, Ernest Rutherford, he discovered the nucleus where the protons, didn't know about neutrons yet, but the mass of the atom was in the nucleus. Electrons were somewhere outside of it. They weren't really organized. Niels Bohr had that famous, model, the first quantized model, where you had these positive protons. There's neutrons in there too, but more important, these electrons orbited the nucleus in shells or orbits, and their distance to the nucleus determined their energy levels. Right? He was the first to talk about the quantized, the energy level, the exact energy level requirements that electrons have. Electrons, of course, that exist closer to the nucleus because they feel the positive of that nuclear charge more. They have lower energy. Electrons that exist farther away, and they could be the outermost, could be the valence. They have higher energy because they're farther away. They don't feel that positive. Okay, so you need to know that the circular paths that everyone wants to think about, all right, in these questions is the Niels Bohr model. That's not the current model of the atom. Okay, the idea that the electrons are loosely packed in the nucleus is in no one's model. Electrons are never in a nucleus. The nucleus was discovered by the gold foil experiment by Ernest Rutherford, shooting the alpha particles. So this was never discovered, electrons in a nucleus, because the nucleus was positive because of the protons. All right. And electrons densely packed in the nucleus for the same reasoning does not make any sense. So a lot of people would pick 3 here because they always think of the atom as electrons going in circular orbits, and all chemistry teachers use this Niels Bohr model to explain the energy levels, and sometimes we do it too much. So Niels Bohr was correct that the atom was quantized, had exact energies based upon the electrons what distance in these orbits. What he was wrong that those electrons didn't travel in circular orbits, but he was right that the electrons did have distinct energy levels based upon shells, based upon distance. So that's really a reason why a lot of people would pick 3, but it's not the correct answer. The wave mechanical model states that, hey, we've got a nucleus, okay, that's positive, whether you understand that neutrons were there or not yet. And these electrons, okay, were in these areas based upon their idea that they make an electron cloud. We don't know exactly where they are at any one time, and we use something called probability. Now, this is not in your question, but you should know wave mechanical model uses probability. That's kind of a catchphrase to discover where the atoms are. Okay, and 2, it also treats electrons acting as particles and, more importantly, as waves. Now, people say, what kind of waves do they make? Well, waves of probability. It's kind of a difficult way to understand the current model, but that's what they talk about. They act as waves. And the 3, and the biggest thing is that electrons don't exist in orbits, but because Niels Bohr took the atom to a new level, and the current model still uses most of what he discussed outside of the orbits, they just use the same word and added orbital. Okay, so orbital is a catchphrase that tells you something about the current electron cloud model. By the way, the wave mechanical model could also be called this electron cloud model too. All right, so be aware of the catchphrase orbital, probability, and waves for the wave mechanical model. And that's why choice 4 is the best answer here. Moving on to number 4. Number 4, when ground state electron in an atom moves to an excited state, the electron does what? Okay, first of all, I hear the word atom. I always think neutral, so it's not an ion. Okay, the ground state means kind of like if you're grounded at home, you're in trouble. You're grounded. We used to say that. Okay, I'm getting older now. Maybe I don't say that anymore, but grounded means you couldn't go anywhere. Ground state means the lowest energy. So the lowest energy an electron can have. Now, the lowest energy would be electrons that exist closer to the nucleus, because a nucleus is positive because of the protons, and it feels the what? The negatives outside. Now, an excited state would be where, man, this thing's got energy, highest energy. Now, highest energy would mean that you're farther away from the nucleus, okay, or that you were given energy to pull away. Let me give you an idea of what I'm talking about. So we know the nucleus is positive because of the protons. There's neutrons in that very small nucleus, but we know that there are shells, okay, and we're just going to use the circular orbits as an example, and I'm going to draw 2 shells. Okay, now these are based upon distances, so we're going to have an electron existing here and an electron existing here. Okay, now we should know, based upon proximity, electrons closer to the positive. Remember, electrons are negative, protons are positive. And this one being closest, this means that this shell right here is going to have the lowest energy. So the lowest energy. And you should know lowest energy means stable. Things that are stable in your life, you don't think about lowest energy, but you probably think about they're always there. If you've got a big rock on your yard, or things that are stable stay in that state because they don't have enough energy to change that state. Okay, so people that you can depend upon, you can think about as being stable. They're always going to be there for you. Okay, now things like electrons that are farther away from the nucleus, like this electron here, we're going to say have higher energy. Okay, and we say that's unstable. If you've got high energy, that normally means that you're going to do something with that energy. Okay, and so electrons that are farther away are unstable. Now, back to the question, why do I care? Well, because in the question it says, when a ground state electron moves to an excited state, what does electron do? Well, okay, so if I've got an electron that's closer to the nucleus here, all right, let's talk about this electron here, and if it is given energy that gets it exactly to this point, that's why it's quantized, it can't just go there, it needs to have a minimum amount of energy, and it can leap to this shell. Okay, it needs to absorb energy because it's got to overcome this positive. So there was an absorption of energy when you move away. You need energy to move away from the positive, my friend, in chemistry. And then this electron will be excited. And the reason why it's excited is because it's in a high position, and wait for it, okay, there's no longer electron in this position there. Okay, there's an ENT. I think I erased a white there. So there's no longer an energy, there's no longer an electron here because it was what? It jumped. Okay, and there is a low position available for an electron, and things in nature like to move back to lower positions. A rock on top of the hill moves to the bottom. Water moves from high to low. Energy moves from high to low. So now we've got something with a high energy, and okay, it'll eventually jump back. So any case, back to the question, when a ground state lowest energy electron, which we now know is close to the nucleus, moves to an excited state, the electron had to do what? It had to absorb energy. Excited means having high energy, and it moves to a higher energy state. Okay, so it, again, for you, this was a ground state right here. Ground, lowest energy. This is excited. It moved to a higher energy state. Okay, so it's important you understand that. All right, so number one is number 4, I should say. Number 1 is the correct choice for number 4 because absorbing energy means you're going to pull away, okay, and be farther away and exist in a higher energy orbital. You have to have this diagram in your head. And as I'm here, why not go over it? Eventually, this high energy electron is going to jump back to its low energy position. And because it has high energy being farther away and it's going to go to low energy, it's going to give off that energy in the form of light or spectrum. And that's where we do the bright line spectrum. The type of light that gives off gives us an inclination of how much energy is being released. Okay, any case, question 4 is number 1. On to number 5. Number 5, which statement describes a chemical property of iron? Okay, whether you know iron or not, iron of course is Fe on the periodic table, but you don't need to know any of that. The chemical properties and its relative, or its its antithesis or opposite, I should say, is the physical property. They love to pit things against itself on these tests. So the physical property versus the chemical property. I should put verse there. That's what this question is about. And because this is a multiple choice question, my friends in chemistry, you can always figure out which one is the one that's different. Okay, but the chemical property is the one about changing into a new substance. Now I say new substance, but a chemical reaction is going to have a new chemical formula. Okay, so in a chemical change, we're going to break bonds and we're going to reform them. And we're going to make products that have a different chemical formula than the reactants. Okay, case in point, I take hydrogen gas and I take oxygen gas. Okay, and I'll need 2 of these particles, and it's going to make 2 water molecules. This is a chemical change. I've got 2 hydrogens. I've got Let's do two hydrogen particles here. These are called elements. Diatomic. Oxygen's diatomic too, but I need one here. These guys react with each other, and what do they make? Well, they're going to make two water molecules that have a different arrangement. Okay, and they're going to look like this. So we're going to break bonds right here, and we're going to form new ones. And we're going to make a brand new chemical formula. We had H2, we had O2, and now we have the compound water. Water is very different than oxygen gas and hydrogen gas. They have new properties. So a chemical property is really testing whether or not you can change into something new by breaking bonds and forming new ones. So malleability is the property. Can you take iron, heat it, and shape it? Of course, iron is a metal, and it's a property of metals. It is malleable, but shaping iron doesn't change its chemical formula. So that, my friends, would be a physical property. Iron conducting electricity is about how well it has free-moving electrons, but it conducting electricity doesn't change the compound. Copper is in our wire. Think about that. Electricity flows through copper. It's not changing. Okay. Iron has a higher melting point. Okay. The melting, freezing, and boiling point are also physical changes. This is huge. Why? Well, Fe solid going to Fe liquid, okay. Are we changing the chemical formula, party people? No. So therefore, it's not a chemical change. So melting point, condensation point, freezing point, vaporization, all the phase changes are physical. And the only choice here that makes sense is ion reacts with nitric acid. Its ability to react like hydrogen and oxygen react, okay, to make something new. So reacting with another compound to make something new is a chemical change. That's why number 5 is 3. On to number 6. Number 6. Diamond and graphite are two forms of solid carbon. That means the chemical formula of diamond, okay, is carbon solid, and graphite is also carbon solid. That's right. All right, so we know diamond is something that we can wear in jewelry. Graphite, of course, is something that we use in our pencils. People say they're lead, but they're not. They're graphite. So there are two forms of solid carbon. Okay, now clearly diamond and graphite have different properties. All right, so if they have different properties, I say this statement over and over again. Structure is king. We know that if you change the chemical formula if you compare molecular formulas, a different arrangement of atoms in compounds will give you different properties. We also know from organic chemistry, if we change the structure with the same chemical formula called an isomer, will have different properties. So we know that the structure has an effect on the property. So in this case, because they have the same chemical formula, it must be the structures are different. Different crystal structures have different properties. So that's why 1 is your answer. Okay, structure is king. So if you change that physical crystalline structure, you will change the properties. Like I said, diamond and graphite are exactly, okay, the same atoms bonded to each other, but they bond in a different arrangement. Will give them a different set of properties. Okay, so these are called allotropes. Okay, but nonetheless, this is a classic question that comes up a lot. All right, structure is king. Change the structure, change the properties. On to number 7. Number 7, which substance? Substance. We should need to know what that is. A substance, my friends, in chemistry is either going to be an element which differs by their proton number, right? So element or a compound. And a compound is two or more different elements bonded together. So which substance can be broken down by a chemical change? Well, we know that elements cannot be broken down, okay, because they're the simplest form of matter. Elements are a group of the same type of atoms. For instance, all right, if I've got neon atoms, okay, they are made up of the same number of protons. But if I have water, everyone likes to use water, okay, you notice it's an H bonded to an O to what? We can break water down into what? The individual elements. So what we're looking for, guys, in my question is a compound. All right, we need something that we can break down. So if you don't know what a compound or a name of the elements, table S, my friend, is the most underutilized table. If you go to table S, you'll find cobalt listed as an atom. You'll find krypton listed as an atom. Manganese as an atom. In your organic part of your course, you should understand that ethane is a compound. Remember, eth is 2 carbons from table P. Ane means a single bond between them. Okay, so carbon must make 4 bonds. 1, 2, 3, this is 4. This carbon makes 1, 2, 3, 4. And so this is C3H8. Okay, which is a saturated hydrocarbon, but more importantly, it's 2 or more different what? Elements bonded. It's a compound, and compounds can be broken down into their individual elements, whereas 1, 3, and 4 are just elements already. Okay, so it's important that you understand that question. Sometimes they'll flip it, which substance can't be broken down. So if it's can't, okay, remember this is can, we'd be looking for elements. Elements are the simplest form of matter in this course. And of course, compounds are 2 or more different elements bonded. All right, hopefully that helped there. So on to, so ethane, of course, is the answer. And on to number 8. Number 8. I got it circled there. Now, based on table I, which equation represents the conservation of mass and energy? All right, my friends in chemistry, you should know that every time a reaction is written with its energy, you should know that mass, energy, and charge are always balanced. Okay, I know the charge part isn't part of this question, but just be aware that all those 3 things are involved. Now, in this question, they want to know which one is the conservation of mass and energy being followed. So we should understand that the conservation of mass part is balancing. Do we have the same number and same type of atoms on both sides of an equation? So anytime you hear of conservation of mass, you should think as, is the reaction balanced? Right? You spent time making sure that you have the same number and same type. So if you look at choice 1 and 2, you can see on the reactant side, which is to the left of the arrow, I only have 2 oxygens, right? So we have two oxygens there, right? So 2 oxygens. And here we've got 2 oxygens, okay? But we have 2 on the CO2, but we also have an oxygen here on the water. So that's 3 oxygens on one side. So on the product side, which is to the right of the arrow, we have 1 more oxygen than the reactant side. So we are not following the conservation of mass. This is not balanced. We're actually creating an oxygen out of thin air. So we can eliminate this. I don't care about the energy because they said and. So who else is balanced correctly? All right. So, or incorrectly to cancel out in this case. I'm going to eliminate the questions, okay, that I know are incorrect because they're not balancing correctly. Look at number 2. We've got 2 oxygens on the reactant side, to the left of the arrow. Okay, you've got to know that to the left of the arrow is your reactant side. On your product side, to the right of the arrow, let's count oxygens. We have 2 on the reactant side. We just got those here. And notice we have 2 here plus an oxygen here. Same deal. We have more oxygens being produced than we started with. You can't do that. Okay? Every single atom that we have on the reactant side must be the same number and same type on the product side. So we're creating an oxygen out of thin air. That's not correctly balanced. All right. Now if you check out 3 and 4, hey, we have 2 times 2, okay, 4 oxygens to the left of the arrow. And then we have 2 here in the CO2, and then we have, don't forget the 2 in front, there's 2 times 1 there, so there's a total of what? Okay, there's a total of 4 electrons on this product side. So that makes sense. There's 4 on this side. Okay, oops, I got the wrong tool here. I've got 4 on this side, and the 2 here plus the 2 that I got from there. So that's balanced. The oxygens are balanced. And of course, there's 1 carbon, there's 1 carbon, there's 4 H's, and there's 4 H's. So if you notice, everything's balanced. And so is choice 4. The same coefficient 2 there and a 2 on the water. So you can see that choice 3 and 4, they have the same coefficients. Those are the things that we call mole ratios that we help to balance reactions. So they're balanced the same. The only difference now is the energy. Who is showing conservation of energy? And all this means for you guys is that the energy is written correctly in the reaction. Notice we have the energy written in front of the arrow. That'd be endothermic. You need that to go forward, right? You're in front of the arrow. And then we have the energy written after the arrow. Okay, right here's the arrow. So this would be exothermic, right? You need to know that energy written on the product side is exothermic. And then the energy written over here in front of the arrow would represent an endothermic. So that's where you're going to need what? Table I. Okay, and by the way, table I has balanced reactions too. So you could have gone there and seen which of these reactions is exactly written as in table I. But what we should know is that these reactions, 1, 2, 3, and 4, is combustion. It's burning. Okay, we use oxygen with a carbon-based fuel, and we make CO2 and water and a lot of energy. Combustion is exothermic. Now, if you didn't know that, go to table I and let's go there to find this exact equation written balanced and with the right energy. So let's go to table I. I like table I. So here we are with table I. Again, I like this table, but more importantly, the reaction we're looking at is right here. And if we look even closer, okay, we can see that we've got 2 O2s and 2 H2s. So this reaction is balanced as we had in choices 3 and 4. The hardest part, I guess, is that you've got a negative value here for delta H. You should know that delta H is the heat of reaction. It's the amount of energy that changes. That's why that symbol there, that delta symbol, is the change of heat or energy. Is it going into the reaction or out? Because it's negative, it's telling you that it's going out. You're losing money, you're losing heat. If you got negative money or negative something, that means that's how much you lost. And losing energy is exothermic. So the energy is always written on the product side, okay, in exothermic reactions. So you had to know that delta H was negative there. But do you really? Because if we scroll down, okay, they tell you that if something is what? Exothermic, there's a minus sign. You just had to know that exothermic means the energy is going to be after the arrow there. Okay, so a lot of hints there for that question. Any case, it's written just as this is, and the energy is, delta H is negative. They tell you it's exothermic. You just had to know, again, energy on the product side is exothermic. So that's why choice 4 is the answer. Let's go back to our test. So choice 4 is your answer. And again, you have the coefficients in front of the O2 and the H2 to have the balanced reaction, conservation of mass. Energy written in the what? Products area, which screams to you exothermic as it was given in table I. So number 8 is 4. On to number 9. Number 9, at STP, which property can be used to differentiate? That's a very advanced word, but basically differ is in that word. So how does one, how can you tell one from the other? In a 10-gram sample of sodium chloride, hey, that's a compound, 2 capital letters, 2 different elements, from a 10-gram sample of sodium nitrate, another compound. This one is a tertiary compound. It's got 3 different capitals, 3 different elements, but those are compounds. So how can we tell that we have one compound from the other? Well, as I have stated previously, if the formula is different, then the properties, chemical and physical, will be different. Okay, these will have different sets of property, and that's what compounds are. They're different from each other because of that different arrangement. But can we tell one compound from the other by just the mass alone? If I have 10 grams of one and 1 gram of the other? No. Any compound can have any mass, so that makes no sense. And any compound can have what? Any temperature. You can't say, well, NaCl is always going to be warmer than NaNO3. That's kind of silly too. All things can have any temperature depending upon how much energy you give it. Okay. Solubility. Well, that is a property that is unique, okay, to each compound. And solubility is the ability of the water, the solvent, to dissolve a certain amount of each of these compounds. If one can be dissolved in a greater amount, can actually dissolve in a greater amount with the same amount of water in the same temperature, it is more soluble. Okay, so that is definitely going to be your answer. Solubility is a property. It's an intensive physical property, and you don't need those fancy words, but intensive physical property are properties that depend upon the identity, like density. If you had the density of these samples, you could identify them. If you knew their melting points and boiling points and you actually melted them and took the temperature, you can identify them. Okay, going back to the choices, phase at STP, well, these are ionic compounds because they're what? Metals and then nonmetals, or in this case, metal and nonmetal. So these guys are all solids, by the way, as all ionic compounds are at STP. So they're both solids, and you can't being solid isn't enough to say one's different because they both are. So 3 is the answer, solubility. By the way, you have a table, a reference table, table G, that shows you solubility curves of how well these compounds are. I'm going to show you anyway, whether you like it or not, onto table G. So here is table G in all of its glory. We can see sodium nitrate has this curve, okay, has this curve right here as I write over it. And then we have, okay, sodium chloride, NaCl, has this curve. All right, and you could see at these grams here, sodium nitrate at every single temperature in 100 grams of water is more soluble, right? If I compare the solubility, let's say at 100 degrees Celsius, I can see that a saturated solution of NaCl is about 40. And if I talk about sodium nitrate, well, it's going to be greater than that because that line keeps going. Not a great example to get off this curve, but we can see that sodium nitrate would have a heck of a higher amount of solubility. You can see that 150, this is 160, something around 170 there. Okay, so clearly sodium nitrate with a higher curve means that there are what? More grams of it can dissolve in the same amount of water at similar temperatures. Okay, so be aware that you have solubility curves, and it's a physical property. When we dissolve these things in water, they're not chemically changing. All right, they're changing into an aqueous phase. So again, number 3 is your answer there for number 9. On to number 10. Number 10, what is the number of electrons shared between the 2 atoms in an O2 molecule? Well, oxygen is a nonmetal. And when it bonds to another nonmetal, even itself, electrons are shared. These are covalent. Co means they're sharing, cohabitating, right? Electrons. And the reasoning, of course, is they both have high attraction for electrons. But if we draw the Lewis dot structure for oxygen, we're going to draw an O, and we're going to put down all of its valence electrons, right? So we're going to go 1, 2, 3, 4, 5, and 6, and we'll draw another oxygen and draw its valence electrons. 1, 2, 3, 4, 5, 6. And then you say, well, how do I know there's 6? If you look up oxygen in the reference table, you'll see 16 for its mass. You'll see 8 for its atomic number, but below that, you're going to see 2-6. The outermost electrons that are unstable, okay, are your valence. So sometimes I'll just ask for electron dots diagram for an element, and the dots equal the valence electrons. We don't care about these electrons in the inner shell. Don't forget, this means 2 electrons in a shell that's closest to the nucleus, and these are electrons that are farther away. They feel the nucleus less. These are the electrons that have a high enough energy to be involved in bonding. Okay, any case, so what we do is we always start with a bond and then we kind of check as you go there. There's a couple different ways to do this. So what I'm going to do is I'm going to remove this electron, and then I'm going to put that right here. Okay, maybe. Okay, so I'm going to put that right there. And then I'm going to remove another electron. I'll take this one, and I'll, okay, put that right here. Now, I'm going to evaluate what I have so far. By sharing, this oxygen feels like it has 1, 2, 3, 4, 5, 6, 7. And by sharing, this one feels like it has 1, 2, 3, 4, 5, 6, 7. Right? So I can see that this is not going to work because we know 8 electrons fills the octet. And the octet means we want to fill this shell here till it gets to 8. So each oxygen wants to share, guess what? 2 electrons. So we got to keep going here. We've got to add a second bond. One bond is a pair. So I'm going to take that one away, and then I'm going to put that one here. Oh, let's keep it the same color. And then I'm going to take this one away, and I'm going to put that one right here. And now you can see this oxygen, by sharing a pair, feels like it has 8, and this one by sharing feels like it has 8, and both have reached what we call the octet. Now we can also rewrite this as an O double bonding to another O. Okay, my O here is ugly, but we have 2 lone pairs left over. And this would be the same thing if they were to ask you to draw a Lewis dot structure of that. Remember, the lone pairs must be shown. So this one dash here represents 2 pairs. The other dash here represents the other pair. So back to the question, how many electrons are shared between the 2 atoms? Well, they're talking about the electrons in a bond. And therefore, because there are 2 bonds, there are 4 electrons being shared, or a total of 4. Now be careful with this question because sometimes they'll say number of electron pairs. They could have said that. They didn't. And the answer would be 2 there because a pair is a bond. Okay, so just be careful of that question there. Okay, so obviously the answer is total of 4 electrons shared. 10 is 4. On to number 11. Number 11. Which change in both charge and radius occur when an atom loses an electron? Okay, so 2 parts to this. Losing an electron, and of course we know electrons are negatively charged, right? If you go to table O, we'll see that the beta particle is given a 0 mass, an E for the electron, okay? A 0 mass, an E for an electron, and a charge of -1. I can get that right from table O. The bottom number is the charge. And they give it a 0 mass because it's 2,000 times lighter than a proton or neutron, so it's insignificant to the mass of a atom. Okay, so If you lose a negative, we should know that the resulting ion should be positive. You lose negativity in your life, you become a more positive person. And we've seen this in redox, my friends. If we take a metal like sodium, and if it loses an electron, 1e negative, remember we wrote that, it's going to become Na plus. And how do I know? Because your teacher said, hey, the charge on one side has to equal the charge on another. Atoms that hang out by themselves, okay, have zero what? Charges. And this whole side is also zero because it's a positive one and a negative one. This is called conservation of charge. All reactions have it. Redox reactions, it's really in the forefront. Electrons are being passed around. By the way, this is called oxidation. Don't have to know this for this question, but you should know this for the entire test. Everything kind of fits together. So losing negatives makes you positive. So you should know that choice 1 and 2 should be gotten rid of. Easy for me to say. So no negative ions are formed. Negative ions are formed is when you gain a negative. We're losing it. And by the way, for those that were going over another question with me, anything to the right of the arrow is something that is released or lost or produced. So losing electrons is oxidation. Now the question is, what happens to the size? People mess this up all the time. So if I have an atom, and this is its atomic radius, and if it loses an electron, it's going to become an ion. In this case, it's going to be a negative ion. The question is, does it get bigger or smaller? Okay, and I probably should have started this a little better. So let me redraw the atom. Oh, Christmas in July. So let me just go back on this a little bit. So let me write my atom, all right, in a way that I can either go bigger or smaller with it. Okay, so let me go, here's my atom, and then we're going to go to an ion. In this case, it's a positive ion. You may have called it cations. Now, does it get bigger or smaller? Okay, well, the best way to remember this, okay, I'm going to give you how I would teach it, and then I would give you the best way to remember it. If you lose negativity, don't forget we have what? We have positives in the nucleus, and we have electrons outside the nucleus. We know that if you have an atom, okay, I say atom, you say neutral, atom, neutral. Electrons always equal protons. So in the case of sodium, since I started with sodium, sodium's atomic number 11, which means it has 11 protons. Okay, so it's plus 11 in the nucleus. And it also has 11 electrons. Now, they're not all in one spot, but I'll just do a negative 11 for all the electrons that you know, are outside the nucleus. And so that negative and positive 11, negative 11 gives you a total of 0. That's why atoms or standalone elements are always written with 0. You should see the connections between the units here. Okay, so if it becomes positive ion, because you lose a negative, oh my gosh, you can see that the protons are going to outnumber the electrons. So if I lose an electron, well, this now is going to be negative 10 outside the nucleus. Okay, and you could see that a positive 11 is now bigger, so the greater positive is going to pull the electrons in closer, and it gets smaller. A positive ion is always smaller than its atoms or its atomic radius, because the protons outnumber the outside electrons and pull them in. If you don't like this, okay, as a lot of students don't, here's the best way to remember this. I am losing electrons, okay? Think about losing electrons like losing weight. When you lose weight, you get what? Smaller! So we're losing electrons, so the resulting ion is smaller than its atom. And they use this terminology, the ionic radius, the charge of the ion, is smaller than its atomic radius. I'm sorry, the ionic radius, the size of the charged atom or ion, is smaller than the atomic radius, okay, the size of the atom that's neutral. By the way, if you gain electrons, let's look at chlorine, and it gains an electron, that'd be 1e negative, so we call reduction. So if you go from a 0 to a negative, because you're gaining negatives, we get bigger because you're gaining electrons or you're gaining weight. So think about electrons gained and lost like weight. You lose electrons, you lose weight, you get smaller. You gain electrons, you gain weight, you get bigger. Okay, so in any case, back to reality here. Up there goes gravity, and I probably have to owe some money to someone for that. But a positive ion is formed with a smaller radius than the atom, okay, because you lost electrons, you lost weight. Number 11 is 3. On to number 12. On to number 12. Which statement describes what occurs when two iodine atoms react to produce an iodine molecule? So atoms are coming together to produce a molecule. So what does that look like? So we have an iodine atom plus another iodine atom come together. I guess it's more money I owe people. And they make an iodine atom that's bonded to another iodine atom. Okay. Forgive me for the bad art. But we did what? A bond was formed, right? These were free atoms and they were bonded. So two I's became I2. It's a difference. Two of the individual iodine atoms, now they're bonded into one particle. That's an I2. So a bond was formed. A chemical bond. So that needs to be understood. So bond forms. That's why we can get rid of 3 and 4. Bond is not breaking. We're putting atoms together into a diatomic molecule. Okay, now the question is about the energy. All right, what's happening to the energy? Okay, we've been through this plenty of times for my class, but people forget it. Why do atoms bond? Why do chemicals do the things they do? Why does anything do the things they do? Things in nature are trying to get to lower energy. This is so gosh darn important. So the reason why iodine and iodine can form a bond is because this state right here is lower energy or more stable than what? The original state. Things in nature go from high to low. So you should know stable means low energy. And therefore atoms together that can react must be what? High energy. So the reason why bonds are formed is to get to a low energy position. A rock on top of the hill, my friends in chemistry, is going to eventually move to the bottom. It never goes the other way, okay? You know, birds are going to land without putting any energy into. Spontaneously, birds land. But when birds want to fly, they have to what? Use their muscles and energy to fight gravity to fly. These are things you should understand. So anytime a bond is formed, you've got to understand that energy is always released. So therefore, 2 is the answer. Another way to remember this is that after I'm done with this video, we're going to meet together and go into town and break stuff. No, of course we're not. But if we want to go break stuff, okay, we need energy, all right? You need energy to break something, and therefore energy is released when you form it, if you want to think opposite. But think about it. Why do atoms bond? They want to get to a low energy position. And we kind of explained this throughout the course. I don't care who your teacher is. Hey, why does, okay, hydrogen want to bond with oxygen? Well, because oxygen has a single electron that it can share with hydrogen. And why does another oxygen bond with, remember, oxygen has 6 valence electrons, and one bonds with one hydrogen and one bonds to another hydrogen. So why does that happen? Because oxygen wants to feel like it has 8 electrons. It wants to fill its outermost shell. And why do we care about that? Because when you fill the octet, wait for it, a filled shell is stable. Hey, let's go look at the iodine. Iodine has 7 valence electrons. How do I know? Its last number given to you on the bottom of the iodine in your periodic table is 7. It's the outermost. So they both have 7 outermost electrons. You put another iodine together. I'm changing colors, hope you can handle it. I'm going to put its 7 valence electrons, and you can see it's a great match. When they come together, they're both going to feel like they have their what? Octet, which, my friends, is stable. When atoms have that filled octet, they're good. They're not going to react anymore. They're lowest energy. Hey, do we know atoms who don't react because they're already at the octet? Oh my gosh, we do. Those are the noble gases. Okay? All the noble gases, group 18, have those filled either PRS orbitals. More importantly, they have, generally speaking, have that 8. We'll keep it at that. Okay? And that getting that octet is a stable scenario. All right? So that's why all of this fits together. If you don't see this big picture coming together and trying to memorize little facts, this is how this works. So number 12 is 2, on to 13. Number 13, which process can be used to separate a mixture of 2 liquids having different boiling points? Well, if they have different boiling points, they have different physical properties. They are different substances for sure. Okay, so we want to separate a mixture of 2 liquids based on their boiling points. Well, we can't separate a liquid by filtration. Come on, you can't filter one liquid out from another. It just does not work. Okay, when we do filtration, we're separating a solid from a liquid, and it's getting trapped on the filter paper with its very tiny pores. Okay, sublimation, you should be aware, is when a what? Solid goes directly to a gas. That's what dry ice does, right? If you've seen that in your class, CO2 solid goes to CO2 gas. Deposition is another phase change that you have to know, and that's when a gas goes directly to a solid. Snowing is the greatest example. But that's not a separation, that's just a phase change. So if we're just eliminating choices that make no sense, we're left with distillation. But what is distillation? Okay, well, it's where we put, and I guess the famous example of distillation, besides separating crude oil into gasoline, natural gases, kerosene, and diesel fuel, besides that is when we ferment something. For instance, if I take sugar, okay, and add it to some solution with yeast, and basically we make alcohol. Alcohol gets developed. And what we do is we heat off the alcohol and we make liquor from this distillation process, because the alcohol will evaporate before the water does for the most part, and that evaporated alcohol will condense as it cools into alcohol droplets. So we can separate the alcohol from the mixture of yeast and sugar if we're, using grains of those things. And I talk about this thing called fermentation because it's something you should be aware of. We ferment, we get alcohol from fermentation, and it's a reaction you have to know where we take a sugar like C6H12O6, okay, and that could be from grapes. If it's from wine, it could be from, if you're making whiskey, it's from grains, and basically make 2 CO2s, and we make 2 ethanol molecules, C2H5OH. Okay, and the ethanol is, of course, the alcohol that is in our wine, liquor, and beer. And how do we separate that alcohol from the mixture? We distill it, we heat it. And because the alcohol boils at a different temperature, much, much lower than the water and the rest of the, when we say mash, it boils off first, and then we're able to condense it and collect it away from the rest of the material. And in essence, it's the same way we separate diesel and kerosene from crude oil, although they use fractional distillation, but the same concept is held. Number 13 is 2. On to number 14. Number 14. Which name describes a solution of sodium chloride in water? So you hear the word solution, ding, ding, ding. That should represent something you already know. A solution, that's a sodium chloride. So sodium chloride is NaCl. The naming of sodium chloride, notice the ID ending is for the binary, that's 2 different capitals. Metal, non-metal, this is ionic. Okay. And it's NaCl, and if it's a solution, we write aqueous. Now, what does that mean? This is really important, party people. This means that this solid has been dissolved. Okay, in water. So when you hear the word solution in water, we know that the water surrounded the sodium ions in a way that it could actually get in between the water. And you have to draw this, okay? You have to be able to do this for different parts of the test or recognize it. Sodium is +1. You can look that up. And chlorine is -1. And water has a negative end, which is the oxygen, the more electronegative end. It will attract and surround the sodium ion this way. And the positive part of water will surround the chloride ion. In this way, these ions get pulled apart and they intermingle, okay, and get dissolved. So you hear the word solution, you think dissolved. You also think when something dissolved, it is homogeneous. Anytime you make a solution, you have a homogeneous mixture. Okay, so anytime you hear of a solution, you know you've got an AQ. You know it's dissolved. You know water is able to attract it and break it apart evenly so that the first drop is the same as the last. Okay, so we know it's homogeneous. By the way, if it's heterogeneous, it'd be insoluble with water. It wouldn't have an aqueous, and you wouldn't say the word solution, okay? You'd have some stuff on the bottom or floating on the top that you can filter out. But this is going to make a solution where there's no solids appearing because they get in between the water, as I'm showing you with these molecule ion attractions. Okay, now who's the water, who's the solvent, and who is the solute? The substance being dissolved is the solute. So the solute is NaCl. The solvent, these are the chemicals doing the dissolving. They're dissolving by surrounding the ions. Okay, of course, is the water. The solvent is the water. And for those reasons, number 3 is your answer. On to number 15. Number 15, at STP, standard temperature and pressure, given to you in Table A, which property would be the same for a liter of helium and a liter of argon? Okay, so they've got the same volume. What else is also the same? If temperature and pressure are held constant, well, it's at STP. Man, this is Avogadro's hypothesis that stated if you've got two different gases, and we do, under the same conditions of temperature and pressure, hey, they're at STP. They're telling you that. They don't have to be at STP, but they have to be at the same temperature and pressure. You're going to have the same number of particles. Same volume, same number of particles. Now, Amadeus Avogadro called a particle a molecule. So a lot of times these questions will say same number of molecules. Now we know something about helium. It's a noble gas. It's very stable. It has a completely filled outermost shell. So they don't bond. So helium is just particles that hang out by themselves. Argon has the octet rule. Its outermost shell is filled as well. Or at least it has the octet rule to show it's very stable. So it's also a single monoatomic particle. So same volume, same number of particles. Okay? A lot of times you'll hear the word molecule. And of course, if this was H2O or CO2, we would use the word molecules because the example they gave me were noble gases that don't bond with anything. Therefore, they're going to just hang out by themselves and just be atoms. It's the same number of atoms. Careful with the atoms answer, okay? Because just as if I do this, if I was to compare CO2 and H2O, okay, not a great example. How about if I do something else? How about if I do CO2 and HCl? These are both gases. Okay. Now, if they're both 1 liter, okay, and they're both at the same conditions of temperature and pressure, they will not have the same atoms. You can see that for every one particle, there are 3 atoms here, and this particle, there's 2 atoms. And I'm counting capital letters for different elements. Okay, so careful with that. So in any case, 15 is 4. I call this the same problem. Okay, and it comes up a lot. It's Avogadro's hypothesis, but I call it the same problem. Same volume, same temperature and pressure, same number of particles. Normally it's written same number of molecules. Okay, any case, number 15, the answer is 4. Okay, mass, density, and boiling point are not what the Avogadro's hypothesis is about. So on to number 16. Number 16, the melting of an ice cube. Melting, that's a phase change. Is an example of what? Well, all phase changes, my friends, are physical changes. You have to have that down. So, ice cube is ice, it's water, it's H2O, solid, and it's going to go to H2O, liquid, or liquid. Liquids have more energy, so I got solid, I got liquid. Now, my friends, that's a physical change. Why? Because the chemical formula is not changing, right? If you were to break bonds and then reassemble and make new bonds, that's a new substance being made. That's new properties are showing up. All of a sudden you see bubbles, a color change. But here the chemical formula is staying the same. So you got to know that. Okay, all types of phase changes, okay, are all physical changes. You're not breaking bonds, you're breaking intermolecular attractions. Now, is it endothermic or exothermic? Does it require energy or is energy released? You need to know that endo is absorbing. So I always think about the heating and cooling curve. So if I give you the heating curve, the best that I can do here, this is the solid phase. At a phase change, the temperature stays constant or the kinetic energy remains constant, but the potential goes up because we're adding heat at a constant rate. And eventually it all becomes a liquid and the liquid goes up. So the solid going to a liquid, that's the phase change. We should all remember the phase change is where the temperature or the kinetic energy stays constant, but the potential energy in this case is going up. Why? Because the kinetic is being converted to potential. Back to the problem. If this is how we're going, and the way to remember this is liquids have more energy than solids. We know that liquids have more degrees of freedom. They don't have to stay in a crystal pattern. So we know that to go from a solid to a liquid, we have to climb an energy ladder. Liquids have more energy than solids. We know that liquids, you have to melt them. You have to melt the solid. You have to add energy. My arrow is going up. This is an endothermic process. This curve is going up. Why? Because we're absorbing energy. We need energy to melt. And we know it's endothermic because you should also know that endothermic makes the environment become colder. That's important. You drop ice cubes in water, it takes the heat from the water and your temperature of your system drops. But in any case, the energy would be written on the reactant side. This is the reactant side. Needs energy to go forward. Liquids have more energy. And so if I have higher energy here and I have lower energy, the only way to make this work is to add energy. The curve is going up. It's endothermic. All right, so you have to know that solid to liquid, you need energy to go to a higher energy state. It's endothermic. So number 2 is your answer here. All right, on to number 17. Number 17, which statement explains the low boiling point, which means the low amount of energy needed to have a phase change of a liquid going to a gas at standard pressure. So I guess they're asking, why does hydrogen, H2, boil at such a low temperature? Why doesn't it need a lot of energy to go from what? H2O liquid into H2O gas, higher energy. Of course, it's endothermic. It needs energy to go up because gases have higher energy. But the point is, why is it so low? Well, the first thing is to understand, party people, is that this is a phase change. It's physical. The chemical formula is not changing. And if the chemical formula is not changing and it's physical, we are not breaking chemical bonds. We are not forming chemical bonds. We don't have any chemical change. So any use of the word bonds makes these choices incorrect. We're not breaking the bonds here. Party people, this is an H bonded to an H. And it's going to what? An H bonded to an H. We're not breaking the bond here. What this more looks like is if I have two hydrogens bonded together in a liquid, liquids normally have a higher density as they attract each other more. And then when they become a gas, they overcome these attractive forces. This would be van der Waals or London dispersion forces or weak nonpolar forces. These gases, when you give enough energy, overcome these attractive forces. They have a heck of a lot more energy and they exist much farther away from each other. You are breaking intermolecular forces here. That includes the weak forces of nonpolar attractive forces, dipole forces, or H bonds. Okay, so we are breaking intermolecular forces, and if it boils at a low temperature, boys, these must be weak. If you don't need much to break these forces to get them into a gas, they've got to be a weak intermolecular force. You have to know that in a phase change, we're not breaking bonds. We're breaking intermolecular forces, which, by the way, are always weaker than bonds. Do never mention bonds breaking during a phase change. Why? Because we're not making a new substance, because we're not breaking bonds and reforming a new one. So you should also know that low boiling points always have weak intermolecular forces. We have a table, okay? Table H, okay, is a vaporization table, has vapor pressure curves. And as temperature goes up, some liquids vaporize easier. So this would be A and this would be B. And we would say that if you look at the same temperature, temperature is written on the bottom here. As temperature goes up, these arrows go up because they vaporize more. But if I pick one temperature, whatever that temperature what it is, whatever it might be, A has a higher rate of evaporation or vapor pressure than B at the same temperature. So why does A have a higher vapor pressure? Weaker forces of attraction. And by the way, if the atmospheric pressure, which is written in a dotted line, equals the vapor pressure, you got boiling. Who reaches this line first? Well, A does. A has a lower boiling point. Things with a lower boiling point have weaker attractive forces. That's these concepts here. So for those reasons, 17 is 4. On to number 18. Number 18. In a chemical reaction, which term is defined as the difference between the potential energy of the products and the potential energy of the reactants? This is a straight definition, but like things, you can infer this from your potential energy curves. So let's just say we have an exothermic reaction. This is a curve that measures potential energy. That's the energy that's in the chemical bonds. And this will be a time coordinate. So over time, if we start with some reactants, okay, these will be my reactants. And when the products are made, in this case, and I'll write them in, so this would be reactants. And these would be products. Okay, now, party people, we're going to have a little pathway here. We're going to have a potential energy curve, and we should know the difference of where we start and finish. The difference where we start and finish is the change. I can do this. Not the greatest straight line, but this difference right here of potential energy is called the delta H. So think with me for a second. This is an exothermic reaction. The products have less energy than the reactants. Why? Because heat was given off exothermically. So delta H is going to be a negative sign because it's going down. But what is delta H? It's the heat of fusion. Well, what's the definition? Well, if this was a value of 20 and this line here was a value of 100, and this would go down negative 80 kilojoules or something. How did that happen? We need a negative to show that energy was released or the energy change went down. We would take the what? Potential energy of the products, 20, minus the potential energy of the reactants, right? That's the reactants potential energy is all of this right here. That's 100. And that'd give you a negative 20. I'm sorry, negative 80. I can do the math. Okay, negative 80. So don't forget, party people, potential energy of the reactants is this line here. That's too big of a line. Wow. Okay. And the potential of the products is this line. All right. So again, potential energy of the reactants is the energy all the way up to this point. This is the potential energy of the products. And then the potential energy of the what? The change in potential energy between those 2 points is delta H. Because it's going down, it's negative. We want to show the negative to say energy is released, so we subtract those two values. Okay, products minus reactants. Okay, and people get lost in potential energy. These are all potential energy curves. And if we keep going, by the way, this would be the activation energy of the forward. This would be the potential energy of the activated complex, right? So in any case, just a couple of things that you should be aware of. So this is a straight definition problem, but you can infer it based upon your potential energy curves. Any case, for all those reasons, okay, the correct answer is number 1. Heat of, oh my gosh, not heat of fusion, heat of reaction, number 2. Okay, heat of fusion is the energy needed to melt something. Okay, all right, so 18 is 2, on to number 19. Number 19. Which phrase describes what happens to a reaction pathway and activation energy of a reaction to which a catalyst is added? So what happens to the activation energy? We all should know that activation energy is lowered, but what does it look like on a potential energy curve? Okay, so we draw a potential energy curve. I'm going to do an exothermic reaction. The reactants have higher energy than the products. We have this pathway. I'll draw the pathway in blue here. And we know that if we add a catalyst, we're going to change that pathway. It's called an alternative pathway. So it lowers the hump, but does not change where you start and where you finish. So it doesn't change delta H. Don't forget the difference where you start and finish. Okay, this arrow right here is delta H, and for an exothermic reaction, it's negative. But what does a catalyst do? A catalyst lowers that hump. And now what is that hump? Well, the difference to where you start to the top of the hill is called activation energy. Think about it. You love to ride slides. This is a slide. Well, you have to climb it. The energy you need to put in to get to the top, then you can just spontaneously move down by yourself, by gravity. So this is the activation energy. But if I add a catalyst, now my activation energy is a lot smaller. The top of the slide is a lot smaller, which means, of course, I can get a lot more rides in for the same energy. That's how it works. You should also know that it increases the rate of reaction. You get a lot more collisions in, effective collisions with the same energy. So don't forget that the pathway is from where you start into where you finish, and so it's going to be a different pathway. This red line here, okay, this red line that I drew right here is a different pathway. So it's a different pathway, and of course it's a lower activation energy, okay, because you need less energy to get to the top, right? So think of the analogy for a reaction to go. You can't just walk up to a slide, you got to climb the slide. And if I lower the slide, there's less energy I have to put into to start my ride, less energy to put into to start the reaction, okay? Any case, that's what activation energy is. 19 is 4. On to number 20. So number 20, an atom of a which element is bonded to a carbon atom in the amide functional group? So what's the name of the group or the class? Okay, in this case, they don't want the name of the group, they want the element that makes it the amide class of functional groups. So there is a table here, my friends. Table R is your friend. So very straightforward. So let's go to table R. So here's table R in all of its glory. We're going to go find the amide. And so I go find the amide, or was it an amine? I losing track at this point in my life, but all I know is that amine, I think it was an amine, it's a nitrogen. Okay, if you notice, the nitrogen is bonded to the carbon. Okay, and same thing for an amide as well. Nitrogen is bonded directly to a carbon. They give you an examples, guys. Okay, so nitrogen is what's bonded to a carbon right from the reference table. All right, so it was an amide, but bottom line is it's the nitrogen. Okay, right from table R. So number 20 is 2. On to number 21. Okay, number 21. Which statement describes two isomers of butane? Isomer. Iso means same. Okay, just like we hear of isotope, same element, different number of neutrons. But isomer is same molecular formula, same number of carbons, hydrogens, and oxygens, are same number and type of atoms, but different structure. So here's an example of two isomers, and whether it's butane or they're isomers of another compound, they're going to have the same molecular formula. Let's count. We have 1, 2, 3, 4 carbons, C4, and then we count the what? The sticks are H's. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's H10. And this one is C4. And if we count the sticks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10. Remember, the sticks are hydrogens. So these both have the same molecular formula, but they have a different structure, and that is what these are called. These are actually called structural isomers. There's different types of isomers, but for this course, structural. So they have the same molecular formula, but different structural formulas. And by the way, because of their different structural formulas, they will have different properties that you must know. And because of that, they actually will have different names, right? So this is actually called butane, the one above it. But for 4 carbons in table what? P. Ane in table Q for the single bonds between the carbons. This one right here is going to have a 1 carbon group attached to a 3 carbon chain. So this is a prop for the 3 carbon longest continuous chain. There's single bonds between the carbons, so that's an ane. But there's this methyl group, this 1 carbon group, and it's in the middle carbon, so to be on the 2nd carbon, we would say 2 methyl propane. 2 different names for the same molecular formula because they have 2 different properties. Okay, I mean, the properties weren't part of this question, but they will be in some other questions. Again, I'm trying to teach you the concepts behind every question, not just what the answer is. So the best answer here is the same molecular formula, but different structural formulas. What's a structural formula? This is a structure. Shows how they exist in 3 dimensions, or at least 2 dimensions, right? So in any case, 21 is 1. On to number 22. Number 22, which term represents an organic reaction that produces soap? So this reaction is the weirdest of all the organic reactions, but what's nice about this reaction, it sounds like a little bit like what you produce. So soap doesn't sound like esterification, doesn't sound like fermentation, doesn't sound like solidification, which by the way is not a chemical reaction, that's a phase change. But soap sounds a lot like saponification. So it is choice 3, but it's the one where people tend to forget about this reaction. But real quickly, Saponification, we make a soap molecule, and you should know its origins to help you figure out this if you don't see this question this way. So I'm just going to go through this quickly, but soap is based upon glycerol. Glycerol is a trihydroxyl alcohol, and it's got an OH group here. So that's what glycerol is. And a fatty acid's going to have a, I'll just draw one of these. So a fatty acid is going to have that COO group, or that organic acid functional group, and it's going to have this long repeating hydrocarbon chain that is very symmetrical and nonpolar. That's what this region here is. And essentially what happens is 3 of these fatty acids, and this is an organic acid right here, right? And this right here is an alcohol group. And when they come together, the water comes out. So if we take out the OH group here, and then an H, water leaves, and we're going to make a big long bond here, but we're going to make an ester linkage, or an ester, and there's 3 of them that occur. As you can see, there's going to be one here and one here as well. So this is called a triglyceride, and that's what's happening. And so when you have a triglyceride, okay, to break it, we add a strong base. So we're going to add a strong base. We'll add NaOH. That's going to dissociate into hydroxides, and they can break this bond here. Remember, there's 3 of them there, okay? And so you're going to need 3 of these, plus this trihydroxyl compound, which again has 3 of these organic acids linked in these positions here, okay? And what you're going to make is, well, you're going to split these 3, you're going to break these ester linkages, and what you're going to make, I'll draw it down here, is a carbon double bonded to the O, and a negative, and the Na plus part will kind of track that negative, and then you're going to have that long hydrocarbon chain. This is a soap molecule. And why is it soap? Well, it's got a polar head, and it's got this non-polar tail, so it can still interact with water like dissolves like, but it also interact with the fats and be able to pull them away. All right, and you should recognize that because there are 3 of these triglycerides, so there's 3 of these esters that are bonding, there's going to be 3 of these molecules. So you're going to take 3 sodium hydroxides, 1 triglyceride, huge molecule. You're going to break apart into 3 of these, and then you're also going to return the glycerol molecule. So you're going to return that glycerol molecule before so it's going to be a trihydroxyl alcohol that returns. Okay, so you never have to write it, but you just have to be able to identify it. So I just wanted to kind of go over that, as opposed to just saying, hey, the answer is 3 because it sounds like soap. I don't think I'm doing my job there. So you should be able to identify it based upon a huge organic molecule, breaking apart into 3 distinct pieces and a trihydroxyl. I think you can definitely identify that. All right. If I just kind of get rid of this, you should know esterification is an alcohol plus an organic acid. The water comes off. It's kind of exactly what happens when you do make a triglyceride. It's not the name of this reaction because we start with a triglyceride. Okay, fermentation is where we take a glucose, and of course we do what with it? We break it apart into 2 CO2s and 2 ethanol molecules. It's anaerobic respiration. And then we have solidification, which we talked about before, is not a reaction. So again, let's go over esterification. Esterification is take let's say this organic, this would be vinegar or ethanoic acid, and let's make ethanol, CH3OH here. And what's going to happen is the water is going to come off. Water is always a product, so let's get rid of that. and then a bond is made. Again, I'm not sure if I can pull these together. Oh, cool. I can do that. And so there's my ester linkage. And my ester is right here. That's the ester functional group. And we name the ester by the alcohol part. Okay, the alcohol part, let's do a different color. It's right there. The alcohol part that has the O and an H. This, of course, is the acid part because of the carbon double bond to an O. So we name that, of course, with the alcohol goes to be methyl. We always name the ester with the alcohol part first, and then the 2-carbon acid part becomes an OAT, so this becomes eth for 2 carbons. Ane, take the EOA and OATE, and again I get this from table R. And by the way, esters, and of course that's one product. The other product would be water because it came out, dehydration synthesis. And of course, methyl ethanoate is an aromatic compound, smells nice. So again, it's an alcohol plus an acid there, water coming out. Okay, fermentation, I think I've driven this before in another problem, but again, I'm here to review all the concepts as much as I possibly can for you here. So that's an easy one you have to identify. I'll write it again. We have glucose, C6H12O6. Sometimes you'll see the zymase, which is an enzyme in yeast. That's going to break apart into 2 CO2s during this oxidation. Plus, we're going to make C2H5OH. You're going to make 2 of these as well. Okay, and these are, of course, the alcohol molecules. Okay, and that's fermenting is how we make our wine, liquor, and beer using the enzyme from yeast, starting off with sugars that can come from grapes or fruits if you're going to make liqueurs, and grains of alcohols. All right, so in any case, the number 22 is 3. On to number 23. Number 23. In which part of the electrochemical cell does reduction occur? Okay, electrochemical cell is a very general term for either the battery, which could be the voltaic cell. That's an L in there. Or the one that requires energy, the electrolytic cell, electroplating. And you can see the word electrolytic has electricity in it. Okay, so the battery is a standalone device that produces energy spontaneously. Electrolytic cell requires energy non-spontaneous, but they both have anodes and cathodes. And there's a nice mnemonic that you should know. Okay, there's the anox, red cat. Of course, the best way to remember is that the anode is the place of oxidation. So there's the electrode, which is the conductor, the place where oxidation occurs, and then reduction occurs at the cathode, the other conductor at the other part of the cell. So in any case, they're looking for where does reduction occurs? Well, red cat means, hey, reduction. So, or I say reduction occurs at the cathode. So choice 2 is the answer. Anox, red cat, nice mnemonic there. So reduction. And no matter which cell you have, the battery or the one that requires energy in a battery, okay, red cat anox works for both of them. So reduction is always at the cathode, no matter whether you have the battery or not. And oxidation always occurs at the anode, again, whether you're on the battery or not. So it's a nice way to remember that. 23 is choice 2. On to number 24. Number 24. Which energy change occurs in an operating voltaic cell? Voltaic cell is your battery. Gotta know that. Alessandro Volta made the first battery when he argued with Luigi Galvani. So it also could be a galvanic cell, but they're a battery. And what do we do with batteries? We take chemicals that will react spontaneously, and they're going to make electricity. Isn't that what a battery does? You put chemicals together and you make electricity. All right, so essentially, that's choice one. I don't know much more to explain about that. But so the chemical energy might get you confused, but you're going to put chemicals and use the energy from the chemicals to make electricity, choice one. All right. But the other cell called the electrolytic cell, the one where you need electricity, you put electricity into that system and you make a chemical change occur. So the electrolytic cell is you need a battery to make the chemical change. So that'd be electricity into chemical energy. So choice three would be the one if we were talking about electroplating or electrolysis, okay? But of course, we're talking about a battery. We're using the chemical energies from the chemicals reacting to make electricity. So number 24 is choice one. On to number 25. Number 25, which substance is an Arrhenius base? People hate this question, like I remember these names, but I always say Arrhenius sounds like the easiest. So the Arrhenius definition is the easiest definition. I know it's not quite rhyming, but hey, that's the best I can do. So what's the easiest definition of a base? Well, there's also the easiest definition of an acid. The best way to remind yourself is go to your tables. We have a table that gives me acids and bases. Okay, so we're going to go to table K and L to look up the Arrhenius base and then acid definition. Let's go there. So table K gives me all the common acids, the Arrhenius definition of an acid, and I know they didn't ask for this in the question, but look at the H in front. Look at the H's in front. Acids, the easiest definition is we give off these H's. Now, of course, we don't give off H's, we give off H pluses, but it's easiest to remember that H pluses are given off from acids. So to be an Arrhenius, the easiest definition, you have H pluses. If an H in front will tell you you have an Arrhenius acid. It's that easy. Now we've got bases. The Arrhenius, or the easiest definition, the first three are, to be a base, you have hydroxide ions come off. All of these three would produce a hydroxide ion, which we know increases the pH. This is not an Arrhenius base because it doesn't have a hydroxide. Now, who has hydroxides? Salts, some form of metal who is positively charged, who attracts the hydroxide. So it's got to be an ionic compound, metal and a hydroxide. You cannot pick something with a carbon and an OH because that's an alcohol, that's a covalent bond. Covalent bonds, with the exception of acids, don't dissociate into ions. That'd be a molecular compound. You're looking for a salt, an ionic compound, okay, with a metal in front bonded to this polyatomic ion called a hydroxide. So if you forget, my friends, in chemistry, okay, the easiest definition, different color, okay, is one that has hydroxides in it that are given off, the OH minus. And table L can help you remind you. So the top ones for bases have how OH minuses are given off. For acids, H pluses. It's just that simple. Back to the problem. So we're looking for a base, and so table L shows us we need a metal with a hydroxide ion. There's my OH with a what? With a metal in front. Okay, Mr. Grotsky, I see the hydroxide ion here. Yeah, but that Cu group there is an acid group from table R or table K. Table K actually has this acid posted as an acid. We're looking for bases. So that's not the answer. And this has an H in front. This would be an Arrhenius acid. Gives off an H, the easiest. This is just a salt. Okay, so choice 3 is the answer. I got a metal, Li, and a hydroxide ion. So number 25 is 3. Don't get those wrong again. Arrhenius, the easiest. Table L helps remind you. On to number 26. Number 26. Which statement represents neutralization? Well, in the word neutralization, hey, we see what? Neutral. And neutral is when we have what? We have the H pluses or the H3O pluses. They're synonymous, which means they're the same thing, equal the hydroxides. And that would give me a pH of 7, neutral pH. So we need to have what? We need to have equal amounts of these. Okay? So it has to be an acid-base reaction. And so neutralization, and I'll give you a great example because it comes this way too, even with words without it. Here's an acid, H in front. It's an Arrhenius acid. Here's a base. We've got that metal with a hydroxide. And we know what's going to happen here. This is going to break apart into H plus and Cl negative. Remember, acids are electrolytes. This is going to break apart into Na plus. It's also an electrolyte. They break apart into free ions and conduct electricity. And so what's going to happen, party people, is this positive is going to hook up with this negative when you pour them together. And what you're going to make is you're going to make water. And this negative will hook up with this positive, and we're going to make salt, or NaCl. It's really a double replacement. But so an Arrhenius acid and our Arrhenius base react to make water and salt. I'm looking at choice 1. It just couldn't be any easier. Okay. The other question says an acid and a salt react to make water and Arrhenius base. No, neutralization is about acids and bases reacting themselves to make a safer compound. Acids by themselves are very dangerous. They can break bonds, decompose bodies. So can bases by themselves. Okay? But when you react them together, they just make salt water. Okay? So the best answer, that just makes, and again, you have to know this, acid plus base makes salt and water. It'd be written that way too. And you should be able to predict the compound that's made here. Why? Because the ions will double replace. Right? So this H plus will hook up with this minus and this here. So you should be able to predict that as well. All right. So number 26, okay, is one. On to 27. Number 27, a tenfold increase. Now, what the heck does that mean? I don't even know why they use that kind of language, but a tenfold means 10 times. It increased 10 times, okay? Because they could use the word hundredfold increase. That would increase 100 times. Okay, so we've got hydronium ion concentration from table E, or from your acid-base unit. Notice the last 3 questions have been a cluster of acid-base questions toward the end of the year. This is the H3O plus ion, which is synonymous with H plus. So we know that this comes from acids. And if you have a lot of these, they make the what? pH go down. Okay, so acids produce H pluses or H3O pluses in solution, and they drop the pH. So if I'm going to increase my hydronium ion concentration, what I'm really doing is I'm increasing the acidity. Okay, I'm increasing the acidity. Okay, and therefore the pH is going to drop. So you're going to have a decrease in your pH. Okay, because pH, that little p means take basically the positive value of the exponent of the H plus, right? So that's really what happens there. So there's going to be a decrease. All right. Now, by how many units? Well, you need to understand that, let's just pretend I have a pH equal to 3. The concentration, the molarity of the H plus or H3O plus would be 1 times 10 to the negative 3. If I've got a pH of 2, remember what pH is. It's the positive value of that exponent. So the concentration of a pH of 2, the concentration of, the H3O plus or the H plus, which pH is based upon, would be 1 times 10 to the negative 2. And I hope you can see that. Hey, that's because positive value of 2. Now, you should see that 1 times 10 to the negative 2 is 10 times bigger than 1 times 10 to the negative 3, right? It's getting closer to being a number less than 1, okay? So this number is larger, and it's larger by 10 times. And if you don't see it, this number right here is 0.001. This number here is 0.01. So you can see that this number here with a pH of 2 that represents it is 10 times, okay, is 10 times larger, okay, and therefore more acidic. So we would say there's a decrease because we're adding an acid. That's an acid component. And every single unit in the pH scale is a 10 unit change. For instance, if I went from a pH of 3 to 1, it would get acidic 100 times because that's what basically a 0. All right, so that is a 2-0 change. Put 2 zeros, right? If every single integer or number on the pH scale represents a 10 times change, if we're going to go from 3 to 1, we are changing 2 zeros. Okay, if it's 10 times 10 is what? 100. All right, and if we went from, let's say, 4 down to 1, we can see we changed 3 zeros, which is 1,000. Okay, so remember, that's the reasoning is because the pH scale is based upon an exponent base 10, which changes every time there's a 10 times change. All right, so in any case, choice 2 is the answer for number 27. On to number 28. Number 28. Based on table N, hello, go to table N. Which particle is emitted by a radioactive decay of francium-220? So let's go find table N, which I call table na, hey, goodbye. Normally it's the last table that people study, but it is connected in conjunction with table O. Okay, so we're gonna look up francium-220 in table N. Let's go. So we have table N, and we're gonna scroll down to francium-220, and there she is. All right. And there's a half-life, but look at this decay mode. Okay, so the decay mode is this little symbol. Now, if you don't know what that symbol is, we're going to go to table O to check it out. And you go find that symbol, which is really an alpha symbol in the Greek letters. So it's an alpha particle, which is a helium nucleus. That's all it is. So francium-220 gives off an alpha particle to get more stable. It's radioactive decay. We're in the nuclear part of the test here. Let's go back to our answer booklet. So the type of radioactive decay is alpha decay. They could say that, or the alpha particle is the type that was emitted, a helium nucleus, because it had too many protons. It had an unstable nucleus. Okay, I know it's not part of the problem, but in radioactive decay or nuclear chemistry, in this case, by itself, an unstable nucleus that has something wrong with it, in this case, too many protons because it's beyond atomic number 83, got more stable by changing its nucleus by emitting an alpha particle. That's important. In any case, 28 is 1. On to number 29. Number 29, which type of reaction releases the greatest amount of energy per kilogram of reactant? Don't get lost with the per kilogram of reactant. You're just saying, hey, which of these choices represents a reaction that gives off the most energy? Don't make it complicated. Now, they love this. The Regents loves to par nuclear equations with what? With chemical reactions. And listen, the last part of questions 27, 28, and 30 are normally the nuclear equations. We go through the choice, question 1 through 30, that goes from atomic structure all the way to the nuclear part, which is normally people's last unit that they teach. So if you look at these reactions, acid-base reaction is a chemical reaction. Organic reaction is a chemical reaction. Redox reaction is a chemical reaction. A fission reaction, hello, that's a fission nuclear bombs, or those are the reactions that are in nuclear reactors where a small amount of fuel, like uranium-235 or 233, can, when it's split by a slow moving neutron, can produce a lot of energy. It can make a bomb out of it or a reactor. But nuclear reactions always give off greatest amount of energy. And that's why they said the bomb dropped on Hiroshima, okay, in World War II to end it, had more energy than every bomb dropped in the World War II, just to show you how much energy is in a nuclear reaction. So again, there was one nuclear reaction compared to what? 3 chemical reactions, and you're in the nuclear area of the test. Notice number 30 is another nuclear question. All right. Now you should also know that in fission reactions or other nuclear reactions, you should also know, as I'm just talking about it, mass is converted to energy. This is called mass defect. We don't have that in regular chemical reactions. And the more missing mass, the more energy given off. Because nuclear fusion is another nuclear reaction, and it actually gives off more energy. That's the hydrogen bomb. And that's by taking light nuclei and slamming them together. Fission takes a large nucleus and splits it into smaller pieces. But fusion actually has more energy released because there's more mass missing, or more mass converted to energy. Some of the things that you need to know. Any case, this question was about number 2 being the answer because it's the only nuclear equation out of the 3. All right, on to number 30. The last question of this 1 through 30 part. Number 30, which risk is related to the radioactive isotopes, radiation, used to generate electricity? So we're talking about nuclear reactors, right? Nuclear reactors. And a nuclear reactor uses nuclear fission, splitting the atom, meaning we take a large unstable nucleus, uranium-235, uranium-233 is only 4 fissionable, and we add a neutron to that, mass of 1, no charge, and then it splits into atomic numbers far less than 92, and splits into smaller nuclei that are more stable, and it could up to 3 more neutrons. So we're splitting a large nucleus with a slow-moving neutron into smaller pieces. This could be krypton, barium, there's a lot of different combinations, okay? But this is done in a nuclear reactor. Why? Well, a small amount of fuel gives you a lot of energy. That's one thing. You don't give off CO2. So therefore, and we're not also giving off any chemicals to the environment that can contribute to acid rain. Acid rain is normally contribute to the byproducts of burning fossil fuels. So we're not burning fossil fuels, and so therefore we're not increasing the amount of pollution in our air, like sulfur-based products that come out of burning gasoline. So we don't have that type of problem. Depletion of the atmospheric ozone is usually with, CFCs or chlorofluorocarbons, where you have carbon-based products getting cleaved off, and they cause a mechanism by which the ozone, the O3, gets depleted. That's not what we're doing here. We're not giving off any pollution. So 2 and 3 are about the fact that we're giving off some kind of pollution, and that's actually not what nuclear reactors do. That's the one thing they don't do, is they don't give off any pollution, or they don't give off any CO2 by that matter. So they're not giving off any greenhouse gases. Okay, that's a positive. And they don't what? They don't contribute to depletion of fossil fuels because you're not using any. Okay, so the risk or the danger is that this reaction could somehow in the nuclear reactor become uncontrollable, or it could not be slowed down. We try to slow this reaction down to gain more energy and not have an uncontrollable effect. This is a controlled or non-chain reaction here. So exposure to nuclear emissions is a risk because you can have something called a meltdown, where the nuclear reactor, for many different reasons, runs too hot and can melt out the containment walls. And we've seen examples of these through the history of time. Chernobyl, of course, is a big event. The Fukushima ones in Japan, and of course, we've had our own small incidents in the 3 Mile Island accident. But in any case, you should be aware that the possibility of a meltdown in the reactor, if we don't control that reaction, could burn through the containment wall and expose, our surrounding environments that people live in with nuclear emissions that are mutagenic or dangerous. Okay, so in any case, choice 4 is the answer. And that concludes the 1 through 30 that goes through the entire curriculum. All right, and then we're going to restart this now with 31 through 50. All right, in what we call B1 with the 2-step question. So on to 31. Number 31, first question of the B1 section. These are the 20 multiple choice questions that, of course, are supposedly 2-step or a little more difficult than the 1 through 30 that we did. But 31, which Lewis dot diagram represents an atom of nitrogen in the ground state? So ground state means that electrons are filling from the lower energy position first before they fill higher energies. Okay, and we should recognize that a ground state configuration, okay, for electron dot diagrams represent the valence electrons. So let's go to the reference table to know the electron configuration and the valence electrons for nitrogen. Let's do that now. So looking at our periodic table, we can see nitrogen right here in the middle, and its configuration is 2-5. Now what does that mean, party people? That means that we're dealing with, okay, here's our nucleus, okay, and then we've got 2 electrons, all right, if you think about shells of electrons, in the first shell closer to the nucleus, and then we have the outermost electrons, or 5 electrons in the outer shell. And these are the ones that are higher energy, the ones closer that feel the positive force of the nucleus. Remember, electrons are negative, so negatives and positive attract. So the closer ones, okay, are lower energy. So it's the higher energy ones, the outermost electrons, in this case, the valence electrons, that become the outermost electrons that we use for electron dot diagrams. So it's the valence electrons, that 5 electrons. So the outermost electrons, the ones that have higher energy, represent how many dots. So if we were doing oxygen, I know that we're not, it would be 6 dots. Fluorine would be 7. Notice our noble gas has the 8. That makes them very stable. Having that octet means that we have a very stable, and they're ground state because electrons are going in order. So that's why they said that. If this was an excited state, maybe an electron would jump here, and that would be a 1 electron, and that would be 6, right? We've talked about going out of order, electrons getting energy to pull away. But in this case, they said ground state, so we're just looking for the valence electrons for the dots. So right from our reference table, nitrogen is 2-5. And so therefore, I'm looking for an N with 5 dots. Okay, and easy to see that choice 2 is going to be that answer. Now, something else with electron dot diagrams, we use them to show bonding, but sometimes they'll just ask you to do this in the part 2 section. They'll say, hey, what is electron dot diagram of an element? You draw the element symbol and the number of dots that represents the valence electrons, that outermost number. Something else you should be aware of, that this symbol N represents the core electrons. These are the electrons that are not in the filled energy level, and that would be the 2 and it also represents the nucleus, which is the protons and the neutrons. So understand that the symbol also represents the core electrons, or sometimes they call them the kernel, and the nucleus. Now I drew one proton, one neutron. Obviously, atomic number for nitrogen is 7, so there'd be 7. Okay, but I'm just giving you a representational model there. Okay, so any case, it's just 5 dots. Choice 2 for number 31. On to 32. Number 32. The atomic masses and natural abundances of the 2 naturally occurring isotopes of silver are shown. So we're talking about isotopes. Iso means same. So in this case, we're talking about the same element, silver, but a different number of neutrons. See, silver is silver, okay, because it has the same number of protons, but it has a different number of neutrons. Since protons and neutrons have the same mass, you can see that silver's got 109 has what? 2 more neutrons. Okay, so this is called the weighted mass problem, right? And I can see in this question, sometimes I've seen this as a choice. If you look up silver on the reference table, just to give you some background, if you have no idea how to do this, and I always assume that when I'm reviewing this. So let's go look at silver on the periodic table to show what is its average isotopic mass. You may not have heard that wording, but that's what it is. The mass written for the silver element or atoms have a decimal place that show an average of all the different types of isotopes. Again, the isotopes are a different number of neutrons for the same number of protons, or in this case, silver. Remember, silver is silver because it has a unique number of protons. Let's take a look just to get a feel for this. So taking a look at the periodic table, we can see this big, baddest, boldest number is the proton number, and that is 47, and that's what makes silver a silver atom. If they had 48, it'd be cadmium. If there was 46, it'd be palladium. So you need to know that what makes an atom different from other atoms, or an element different from other atoms, is that proton number. Now we should also know that's also the electron number. If you add up all the electrons, remember this is an electron arrangement of a ground state silver, okay, it would add up to 47 as well because all the positives equal the negatives. But what I'm after here right now is the mass number. This is the mass number. It's got a decimal place. I told you that protons and neutrons have about the same mass, and that mass is called 1 unit or 1 atomic mass unit. It's a relative number. We can't put a scale on it. Why does it have a decimal place? It has a decimal place because they averaged all of the natural occurring isotopes for silver. And the reason why it's 107.868 is that the most stable and highest abundance isotope for silver must be 108, because this averages out to 108, because one isotope of the group, okay, is in greatest abundances. And what they do to get this number is they average all of the different forms of silver, all of the different number of ways it can have extra or less neutrons. That's an isotope with 47 protons. And because we need to know the actual percentages of each of these forms, using those percentages, we come up with this number. All right, it's kind of like, I always talk about this in my class, I use weighted averages. 60% of your overall quarter score is your test grade. So it must make sense that your quarter grade is going to be closer to your test grade than your quiz or your lab grade, because the greatest weight of your score is the test grade. Okay, so same idea. So this is what this question is about. All right, so it's 107.868. What they're doing in this question is showing you, or trying to get to this number, even though it may not come out exactly. Okay, so let's get back to the question. To actually do this averaging of the isotopes to come up with some number like this. So we have 2 isotopes, 107 and 109. Okay, And if you were to do a straight average between these two numbers, you would get 108. Okay, but if you notice, we didn't get 108, we got 107.8 something. Okay, so it was closer to 107 because one of the two isotopes exists in a greater abundance. So how do I do this problem? What we do is we find the percentage of each of the atomic masses, and then we add them together. When you do a percentage, you move the decimal place 2 places. So I'm going to move this 1, 2, and so I'm going to take 106.905. I'm going to times it by 0.518, and then I'm going to add it to the next one. I'm going to take 48.2% of this number. So I'm going to take 108.905. That's the actual, okay, very precise mass of that isotope. And you say, why isn't that a whole number? Because protons and neutrons aren't exactly the same mass. And we times that by 0.482. Notice I moved the decimal place 2 places. And that's the problem, guys. That's it. Take the percentage of each of the exact atomic masses for that isotope and add them together. So which choice is that? Okay. Notice in choice 1, they forgot to move the decimal place over. Okay. This is supposed to be 0.51. And choice 2 is the same thing, except they're adding the percentages. Okay. Now choice 3, okay, we're still, I'm sorry, for number 2, if it's a percentage, that means it's divided by 100. So again, I get rid of 1 because it's got to be 0.51 here and 0.482 here, so I get rid of 1. This might have looked weird to you, as it did to me when I first saw this choice. Number 3, you can see that just because it's 482, they got 106, so that in number 3, what they're doing is multiplying. They're trying to find the percentage of this isotope, which no, the percentage is due to this one, so that doesn't make any sense. They've got those mixed up. And then they're doing the same thing for number 4. They're putting the wrong number with that atomic mass. So if you think about it, the only choice that makes sense is 2. Now, I'm not a big fan of this question because I haven't quite seen it this way, but it's the only choice that makes sense. What a percentage is a 51.8 divided by 100, right? So by putting a percentage there, they're implying 0.518. So that's what that is doing there. Okay, not a big fan of the question, but you can tell 1 you cross off, 3 and 4 makes no sense because they were trying to find the percentages of the wrong atomic mass there. So by process of elimination, 2 is the correct answer. The reason why the percentage works here is we have the right number, and a percentage really is moving that decimal place over by saying that. And sometimes they'll give you choices. Well, they'll, instead of moving this decimal place, let me remove it. Let's put the 0.1 here, right? And they'll just take this and they'll have it divided by 100. Okay, so it's another way to see it. So if I was to move this decimal place, get rid of that, and move it back, if you divide by 100, okay, over that entire expression, it's the same thing. And by the way, this right here is a percentage. So again, I think it's easy to eliminate the wrong answer by process elimination, but that's what that percentage means. And this is a very, very, very typical, okay, problem. And you need to understand the wording, okay, because they can say, what is that atomic mass that's listed on the periodic table? And it is the average of the natural occurring isotopes that exist in nature. Okay, so be aware of that wording, okay, as I showed you. All right, so in any case, 32 is 2. On to number 33. Number 33. It's really important to know where you are in this test. So if we're starting in the early 30s here, that's we're doing the B1 section. You should know that this test goes in order of atomic structure. So, here we are with atomic mass number. I'm sorry, a potassium atom has a mass number of 37. What they're telling you is potassium has a mass of 37. That's a particular isotope. Potassium can have different number of neutrons. They're called isotopes, and for the same element. They're just giving you an example of just 37, okay? If we go to the reference table, okay, we need to figure out exactly what the atomic number is to get the neutrons. Remember, what's unique about potassium is its number of protons, which is the atomic number. That's the number, that's the biggest, baddest, boldest number, and it's one without a decimal place. Let's go to the reference table. So there is potassium, number 19 in terms of its atomic number. Now, if you didn't know potassium was K, by the way, if I jump that idea, table S will tell you that. So if you're not sure what the name and chemical symbol is for a name of an element, okay, please go to table S and you would find K for potassium. But in any case, this is the mass number that has a decimal place because it's the what? Weighted average of all the natural occurring isotopes using their relative abundances in nature. We talked about the I think 32, if you got stuck on that question, how that number is a decimal place because they use an average of all the different types and forms of potassium with different number of neutrons. And they average them out using, how much percentages they exist in nature. It's a weighted average. But here, we needed to know the atomic number is 19. Now, they gave us in the question potassium 37. That's a particular isotope. Notice it's 39 in the reference table. So a lot of people would just say, okay, I know how to get neutrons. I subtract. And if you round this off to 39, which your teacher would do, because that's going to give you what? The most common and the largest abundance in nature isotope. Okay, easy for me to say. 39 minus 19, of course, okay, would give you the 20. All right. But that's not what they're asking. They're asking for 37. Okay, they're asking for the particular isotope of potassium 37. It's still 19 because to be potassium, you have to have 19 protons. Okay, here is the subtraction. All right, so there is what we do there. Now you say, well, how do I know to subtract to get neutrons? Well, my friends, in chemistry, this number is the mass number. You should know that from table O. Okay, neutrons have a mass of 1, no charge. Protons from table O have a mass of 1 and a charge of 1. So these guys have the same mass. So the entire mass of the atom, and if you also look at the beta particle in table O, you'll see that the electron, which is also a beta particle, -1 charge, but they give it a 0 mass, even though it really does have mass. It's 2,000 times lighter than these guys. So my friends, in chemistry, it doesn't really add to the entire mass of the atom. It doesn't contribute significantly to the mass of the atom. So very simply, entire mass of the atom is due to protons and neutrons. And if you know the 19 protons, and the top number is what? Protons and neutrons, subtracting gives you the neutrons. Okay. So if we do our subtraction, very simple, 17, 8, right? So you're going to get 18 neutrons in this case. But they were talking about potassium 37, not 39. Okay, we needed to go to the reference table if you didn't know the atomic number. Who knows? Unless you're memorizing them on the weekend, and that makes you very cool. Not. Okay, back to the question. So here we are, and it's atomic number 19. And as we said before, okay, do your subtraction, and you're going to get 18, and that's why choice 2 is the answer. Okay, they were very nice because I would think they would have given 20 as a choice here, but they didn't, so it becomes a really easy problem. All right, so on to number 34. Number 34. At room temperature, a student determines the density of a sample of nickel to be 9.79 grams per cubic centimeters. The student determines, that's the experimental value. Based on table S, they're telling you where to go. What is the student's percent error? So I guess we gotta go to table S and look at the percent error. Okay, now if we're trying to figure out the percent error, we're going to find out that we're going to need a known or a theoretical. All right, and that's where they're kind of letting you go to table S there to find that. So what they're not telling you is that there is table T to know what the formula is for percent error. So percent error has a formula. Let's go get that if you have forgotten. You probably have done this in many labs, as my students have also. So let's get that formula first. And again, all formulas for math problems are going to be in table T. That's important that you know it's the last reference table. And let's go there to get percent error if you have forgotten. So there we are with percent error. And we see the measured value, okay, minus the accepted value. So you've got to understand that the measured value is, of course, what the student measured in the experiment. The problem is we've got to get the what? We've got to get the accepted or theoretical value. And they were telling us that table S, okay, has that value. All right, notice we're timesing it by 100 to find a percentage. So we're going to compare what the student found, the measured value, and we're going to need that accepted value. So let's go write down that formula first, and then we'll go to table S to find the known value or the accepted value. Okay, so we've got our formula written down from table T, and we just have to recognize that we're dealing with this measured value, okay, right here. This is our measured value. So let's put that in for measured, right? So let's get rid of the measured, okay, and let's add our 9.79. Okay. Now we need the accepted, and if you forgot, table S gives us a bunch of things. Atomic radius, it gives us melting, boiling points, electronegativity, ionization energy, and also gives us density, right? That's what this is found. We're looking for the density value of what? Of nickel. So let's go find that in table S. So table S, as I said, gives you a whole bunch of things, but we're looking for the density. And nickel is right at the bottom here, atomic number 28, and we're looking for its density, which is 8.90. Again, and that's really all we're doing, looking for that, and of course that is for nickel. Okay, so 8.90 is the known value. That's where they told us to look. Let's put that in our formula. So we're going to put the 8.90 right in for the accepted 8.90. Okay, and we have our equation that we're essentially plugging and chugging. Okay, so no reason to get this wrong. This is a classic either part free response question or a question you see in this part. Okay, so 9.79 minus 8.90, I get 0.89. So I just subtracted these two numbers, and now I'm going to divide by 8.90. So my 0.89 divide by 8.90, I get 0.1. And so this whole expression here is 0.1. I'm going to times it by 100. Okay, if you don't see that, and you're going to get 10%. And that's why choice 4 is the answer. So they gave you everything. You just had to know what you were dealing with. They gave you the what? The experimental value, okay, or the measured value from the experiment. You had to look up the known or the accepted from table S, and of course table T gave you the entire equation. On to number 35. Number 35, compared to the metals in period 2, the non-metals in period 2 have what? Ooh, a little tricky. You have to know what these things are. Okay, so let's think about period 2. Period 2 you should recognize that is going to be row 2. So if you're confused about period 2, we're in the second row, or we're n equals 2, and that's given to you actually, okay, in the reference table, the periodic table. So any case, if you look to the left side of that, you can see that, but that's row 2. Now, what elements do we have? Let's draw those, okay? So we have, just write that down here. In the second, we have lithium. We have beryllium. Don't be a boron, okay? Then we've got carbon. Then we've got nitrogen. Then we've got oxygen. Then we've got fluorine, okay? And then we've got neon. Okay, I probably could have done a little bit better in terms of figuring out my spacing, but what do I know? Well, I know that my metals, okay, my metals are going to basically, okay, be on this side. And my nonmetals are on the right-hand side. Now we know there's a staircase, all right? Boron, there's silicon. Okay, if we go a little lower, there's arsenic. Okay, oops, can't see that. All right, so arsenic is there. So there's a staircase. So you should know that your nonmetals, okay, are to the what? Up to the right above the staircase. There's my nonmetals. And then my metals are to the left of the staircase. So you needed to know where they are in the row 2. Okay, so here's a metal. Here's a metal. The nonmetals I'll do in red. Because boron is on that staircase, it's a metalloid, along with silicon and arsenic, right? So it's a metalloid, has properties of both. So what they were really saying in this question, compared to the metals, or to the left-hand side, the nonmetals, which is the right-hand side, have what's going on here? Okay, well, now that we have established what they're talking about, let me get rid of the staircase here because I want to be able to, write some things here. Let me just white that out. It'll be all white. Don't worry. More bad puns are on its way. Okay, having fun with the puns. Told you. Okay, now, you should know this. Okay, this is atomic number 3. Oh, Christmas, too big. And atomic number 3 is from the reference table. And I put this here because there's some important things you should know. Atomic number 4, 5, 6, 7, 8, 9, and 10. Now, what's so important about these atomic numbers is that this is called the nuclear charge. This is the charge in the nucleus. In the nucleus, you got protons, which are positive. Table O tells you that. Neutrons are there too. Ernest Rutherford in his gold foil experiment said the entire mass of the atom was in a very small space, the atomic nucleus, but the neutrons have no charge. So the entire charge of the nucleus is the proton number. It's also called a nuclear charge. It comes up on tests, so make sure you know the nuclear charge is the proton number. It's not the charge of the atom, it's the charge of the nucleus. Since electrons are not in the nucleus, the charge of the atom, okay, is the number of protons. Now, party people, what happens when you increase the number of protons? Okay, in the same energy level. Because we're in row 2, we're in the second row or the second shell. We're in the same energy shell. Remember, electrons fill certain shells. The first shell holds 2. The second shell holds 8, which is called the octet, which is a stable number. Bottom line is we're in the second row, the second shell. Okay, and we fill that shell with the noble gases. That's why these guys don't bond. But we need to understand something. As we go across, okay, we should know that the atomic radius, okay, starts out big but gets smaller as I go across because the number of what? Protons pulls in the electrons. That's what makes the radius smaller. Okay, so without table S, what happens when you go across period 2? That's what they're really asking, row 2. So compared to the metals, the nonmetals, so the nonmetals are going to have, okay, a smaller atomic radii. We know that. Okay, and because they are small, it's because they have a higher attraction. Attraction for electrons is called electronegativity. You've got to know that. So they have a higher electronegativity because they have a greater number of protons. Even though this question doesn't require everything that I'm explaining, but understanding all of this will help you for other questions that are similar. If I am a smaller radius, That's because I'm pulling in electrons in closer to my nucleus. Why? Because I have more protons. The more protons, the stronger this electrostatic attraction is, and the radius gets smaller. So as there's more protons going across, yes, there's more electrons, but the force of the nucleus in the same shell pulls them in tighter. And therefore, you're going to have a higher attraction. Another word for attraction is electronegativity. Now, the other word, ionization energy, everyone forgets. It's the energy needed to pull an electron away. Well, if you're going to pull in electrons closer, hello, you're going to hold on to them tighter. It's going to take more energy to remove them. So what the best answer here is choice 4, higher first ionization energy and higher electronegativity. And that's totally based upon something you should already know, the trends. But wait a minute. If you didn't like anything I did, you know what you could have done? Wait for it. Go to Table S. Table S. You could have looked up, not tables, but Table S. Okay, you could have looked up every one of these values in row 2 and saw that the ones on the right are going to have a higher electronegativity and a higher ionization energy. Okay, but understanding what I just did will help you navigate similar problems better. So 35 is choice 4, right off table S, but you had to know the non-metals were on the right-hand side of that table, and the metals were on the left-hand side. Okay, so on to 36. Number 36. Which form represents calcium hydride? Ooh, I see the IDE, and I see a metal in front. Okay, so I know this is a name of a salt, an ionic compound, metal, non-metal. Okay, anytime I see the IDE, I think of a binary naming system. Binary just means two different elements, a metal and a non-metal. I don't care how many of each. That's the IUPAC naming system. So calcium is going to go in front because the positive ion or the metal does. And hydride. Now, if you notice, they have OH here. Now, OH sounds like hydride, but if you look carefully on table E, that would not be the name of that. Let's take a look at table E, which is what I call the what the heck is that table. Okay, so in table E, my friends, we see polyatomic ions. Now, I just said that the naming system for a binary, 2 different elements, ends in IDE. That's true. Now, if we're naming something that has a polyatomic ion, the metal's name would go in front, like the calcium, and then we would just get the name of the polyatomic ion inside. So if you notice, there's a one here that does end in IDE, but that's the hydroxide polyatomic ion. So if I had calcium hydroxide, calcium, okay, we're going to learn is +2 because it's a column 2 element. It's the alkaline earth metals, that second column, column 2, they're all +2. We can see that -1 charge for the hydroxide cluster. I call it a cluster because it's usually a group of non-metals sticking together and has one particular charge. So this thing sticks together. And when you, of course, name these, you have to have this a 0 charge. So basically, it's how many each of these ions do you need to get a lowest ratio formula. That's right, an empirical formula for ionic compounds, metal, non-metal. Okay, so this would be calcium, and this would be, you need 2 hydroxides because calcium is +2. This is -1. That's what a negative means. So you need 2 of those negatives to equal 0. We throw parentheses here to show that that is calcium hydroxide, to show that we have 2 of these -1 ions to balance the 1 calcium +2. So that would be the formula of calcium hydroxide. But party people, they gave you calcium hydride. So there's no hydride written here. If you heard of oxide, so usually when you hear an IDE, it usually means you have a binary compound. So the hydride just means hydrogen. Okay, any case, if you don't know where I got the +2 for calcium, let's go there. So again, calcium, this upper right hand corner charge tells you the charge it likes to become. And notice it has 2 valence electrons. You should know that metals to the left of the staircase love to lose their valence electrons. to, guess what, have an 8 to get stable. The octet rule is a driving force. Okay, notice potassium wants to lose 1, but the point of the problem here is that calcium likes to become +2. Okay, and it wasn't a hydroxide, it was a hydride, so it was just a hydrogen. So let's check out hydrogen. Okay, so hydrogen, if calcium only has one choice, the hydrogen has to be -1. So calcium is +2, hydride is -1. What combination is going to give me an overall 0? Well, that's going to be 2 hydrogens. If you don't see that, you can always use the crisscross method. And that was the group that had that song, Jump, Jump. Okay, any case. So that would be calcium with one of them, and of course 2 hydrogens. Because it's not a polyatomic ion, that's all you need. Notice hydrogen can be negative. It's not a metal. Okay, so it could gain an electron to get its filled number. Okay, so in any case, they wanted hydride, so calcium H2. Let's back to the problem. All right, so again, hydride, very important, is H, and we need 2 of them because each H is -1, calcium is +2. They were talking about choice 2 here. Okay, this is a polyatomic ion. This is not binary. Okay, and again, the OH, the reason why they did that is because the polyatomic name, that example did have an "ide" in it, so it was kind of confusing. All right, but it, again, the hydride wasn't listed in table E. So if the hydride was listed in table E, you'd have been good to go, but it's not. So therefore we knew it had to be just hydrogen. All right, so 36 is choice 2. On to 37. Number 37, what is the number of moles in a 78.8 gram sample of magnesium carbonate? Ooh, they even gave us the gram formula mass. How nice. So what they want you to do is convert 78.8 grams to moles. That's what they want. So very simply, I'm going to take, always in a conversion, I always write what's given to me first. They gave me 78.8 grams of this compound. I'm going to, some people like to memorize when do I divide or multiply, and I don't think that's really appropriate in my opinion. So I want to get rid of grams. So the unit I want to get rid of goes down here. It's going to cancel because 1/gram, think about it, 1/gram times gram. Now that gram is over 1, so you can see that they're going to cancel. So that's the reason why we put the grams in the bottom. Now what do I want? They want what is the number of moles. So for every 1 mole, okay, how many grams do I have? Oh, they told us that. The gram formula mass is 84.3. So they're telling me exactly what that is. Now, in a separate problem, they could ask for the gram formula mass, which is the same thing as the formula mass or molecular mass. And all you would do is add up each of the individual atoms. Like magnesium, its atomic mass is 24. Carbon is 12. Each oxygen is 16. You times that by 3, add that up, and you would get approximately 84.3. So I've seen that as a separate problem. So they could say, what is the formula mass, which is what we use, okay? It's what we use to do the conversion. So this bottom number is just adding up 1 magnesium. And by the way, I'm showing you this because you could see a problem similar to this, not the same. 1 times 24, hey, that's 24. Okay, hey, there's 1 carbon. 1 times its atomic mass is 12 is equal to 12. By the way, I'm getting these numbers from the atomic masses, the top number. They have a decimal because they're averaging their isotopes. We're just going to round them off. And then we have 3 oxygens in this formula. And E is 3 times the atomic mass of 16, and that's 48. Okay, you add that together. 8 and 2 is 10, I get what? 14. And then I get 4, 2 is 5. And so I get 84. And that's close to 84.3. The reason why I don't get the same answer is because I've rounded. But you can round on the Regents. But I'm doing this because they could have asked for the formula mass. Okay, they didn't. I know, Mr. Grodsky. So just get to the problem, please. All right, well now we just got to do the math. Okay, so let's do the math. Okay, I got my handy dandy calculator, and I'm going to take my 78.8 and divide by 84.3. Okay, Some people don't even see this number and wind up doing that anyway. So I get 0.9347, and there's 3 significant figures, so I should have 3 back. So this 7 makes this go to a 5, so 935, and that's why choice 2 is the answer. So it's just a straight, okay, conversion. And again, to know how to set this up, take the unit you're getting rid of and it goes in the bottom. I never ever memorize when I multiply or divide to go from moles to grams and grams to moles. All right, so number 37 is choice 2. On to number 38. Number 38, given the equation represented below, which type of chemical reaction is represented by the equation? Well, my friends in chemistry, I see an F2 bonded to itself. So it's the same element, it's diatomic, it's one of those Hofbrinkels, that's the mnemonic to remember who is diatomic. And if you notice on the product side, which I call the future, the K bonds to the F and the Cl's by itself. So what happened is F saw K and Cl dancing and it just basically cut in. And it replaced the Cl with just one F. There was just one replacement. The Cl was kicked out and the Kf are now dancing. So because there was one replacement, it's a single replacement, which is a great example of a redox reaction. And how to identify a redox reaction, I look for standalones. Anytime I see a standalone element bonded to itself or not bonded to any other element, those are zero charges, and when they bond to something, they become something other than zero. Therefore, electrons are being passed around. But this is single replacement. To review, synthesis would be, hey, 2 things coming together. A and B makes AB. Decomposition is breaking apart, like decomposing. That would be AB breaking down into its individual elements. Double replacement, okay, would be if you had 2 replacements going on. A great example, let's just make up one on top of my head. Let's say I have lead nitrate, PB, I'll do lead nitrate. Nitrate's a polyatomic ion, plus potassium iodide. And this positive ion would hook up with this negative here. Oh, I tried to change the colors. And this positive ion we replace with the nitrate. So what are we going to make? Well, we're going to make PbI. Now, Pb is +2, I is -1, so it had need a new formula, but they're going to replace. And also, K would go with the nitrate. Nitrate's a polyatomic ion, sticks together. Nitrates are -1, K is +1. So you notice there were 2 things switching partners. That's a double replacement, and that's not a redox reaction. You don't see a standalone. All of the oxidation numbers are staying constant. Any case, number 38 is 3. On to number 39. Number 39. Based on table H, which compound has the strongest intermolecular forces at 60 kilopascals? So my friends in chemistry, what does it mean to have its strongest intermolecular forces? Before we go to table H, let's understand what table H is. It's a vapor pressure table, okay? So what you're going to measure is the vapor pressure of certain liquids and how they change over temperature. Now, my gosh, that's great, but what is vapor pressure? Vapor pressure is essentially the force due to molecules evaporating. So molecules of liquids are in a liquid phase, they're not in a crystal structure, and they evaporate. They don't have to boil to evaporate, but they evaporate. Now, if you give them more heat, they overcome their attractive forces. Notice the dot, dot, dot I'm drawing. These guys are sticking together by intermolecular forces of attraction. They're not bonds. They are significant though. So in order for a liquid to evaporate and provide a force upward, which is we call vapor pressure, they have to overcome these attractive forces. So if you think about it, if these forces are weak, doesn't it make sense they can pull away from each other much easier? And there's going to be a lot of vapor pressure. By the way, vapor pressure, you can think of it as the rate of evaporation. So liquids that evaporate very fast, okay, do so because they have what? An easier time overcoming these attractive forces, okay? So If I'm looking for something that has a weak intermolecular force, if I give it a little heat, the vapor pressure should climb up really fast. Those that have stronger intermolecular attractions would need a lot of temperature, a lot more energy to climb their vapor pressure or their rate of evaporation. So which one has the strongest intermolecular forces? So I'm looking for something that's resisting evaporating. I'm looking for the curve that's more flattened out at 60. I'm looking for the chemical, okay, that has the lowest vapor pressure, or the lowest what? Rate of evaporation for that particular point. So let's go for 60 kilopascals and see which one is resisting evaporating, who has the lowest vapor pressure. Let's go to table H right now. So as I promised, vapor pressure is on the y-axis, temperature on the x. And if we go find the kilopascal pressure, here we are here. So which value do you think is resisting evaporation because they're holding to each other so strongly, okay, that they're going to have the lowest vapor pressure? Okay, so at 60, you can see that they all have the same vapor pressure. We're not looking at the same temperature, but we can see that the line here that's resisting evaporation the greatest is here. Another way to think of it too is that we should know that the vapor pressure upward, when it equals the atmospheric pressure downward, is boiling. So we can see that ethanoic acid is the answer here. It's going to have the strongest intermolecular attractions because at 60 it's got the flattest curve. Or we can also say it's, if the atmospheric pressure is 60, it'll boil at the highest temperature. So boiling is when the vapor pressure equals the atmospheric pressure. Okay, so a couple of different ways to answer this, but the flattest line at 60 is ethanoic acid, which means it's resisting. Look at propanone. This sucker's flying up. Why? Because it has the weakest attractive forces. This is nail polish remover. Ever spill that on a table? Disappears fast, or it feels cold, could evaporate so fast. So ethanoic acid is resisting evaporation. It is the one with the lowest vapor. Well, it's the one that has the flattest curve, so to speak, in this case. Okay? So 39 is number one. This is the curve that resists evaporation. Okay? Any case, if you should also know that a lower the vapor pressure, higher the strength of the intermolecular forces, and therefore higher the boiling point. Okay, that relationship you should have down. And the opposite is also true. If you have high vapor pressure, that'd be like propanone over here, you would have weak attractive forces, and you wouldn't need a lot of energy to match the atmospheric pressure, so your boiling point would be low. Any case, 39 is 1, on to number 40. Number 40. Which particle die represents a sample of xenon at STP? Now, STP is standard temperature and pressure. Okay, we love to compare at those values. Standard temperature on table A is 273 Kelvin or 0 degrees Celsius, and standard pressure is either 1 atmosphere or 101.3 kilopascals. I'm not making this up. Look at table A in your reference table, but that's not really what this is about. This is about what phase is xenon in. They're asking you, is it a solid, liquid, or gas? You should know that solids have a regular repeating arrangement, so these two would definitely be solids. This would be, if you're looking from it as this is the down, this is the middle, these both look like gases to me. Notice they have these particles bonded together or by themselves. Now let's go over something here. You need to know who your diatomic elements are. If elements are bonding to themselves, they're called diatomic elements. And you should know who those are. And I remember them by this mnemonic Hofbrinkel's. HOFBRINCL. All of these guys love to bond with themselves. H2, O2, F2, Br2, I2, N2, Cl2. So you can remember all of your diatomics. Xenon is not part of this mnemonic. So xenon is not going to be diatomic. Now there's another way you can notice that too. Xenon, where is it on the reference table? Let's go there. So if we look at the periodic table of elements, we see our xenon. And you say, oh, Mr. Grodsky, I don't know xenon is Xe, okay? But what can we do? Well, you have table S, okay? And if you don't know what Xe is, okay, you can find out from your reference table. So if we go to atomic number 54, we can see that Xe is xenon. All right, now we're going to go back to table S in a second, but before we do so, let's go back to the reference table, and we should know something about this last column or this last group. These guys right here are the, oh, I really should include helium, right? Bad Grodsky. So including helium, these guys are all noble gases. Okay, what's so special about them is that they're highly unreactive. And the reasoning is they have this octet. They've got a very stable electron configuration. Having an outermost valence electrons of 8 means that they do not like to bond with things. Now there is some little bit of reactivity from krypton and xenon, and that would only be with F, but for the most part, noble gases don't react. So my friends in chemistry, these are the noble gases. Can I say that again? These are the noble gases. So xenon is a gas, and because it doesn't bond with anything, it's monoatomic, which means if I write the what? If I write a particle diagram, it's just going to be one circle or one atom. It's not going to be diatomic because, well, it doesn't bond with anything. And we know it's also not what? It's also not a Hofbrinkel if you want to use the mnemonic. So the noble gases will never be bonded to anything, so you draw them as single monoatomic atoms hanging out by themselves, and they're gases because all the noble gases are gases. But if you still didn't know any of that, we can go to table S, and let's go find xenon again. And table S is the most underutilized table, and I'm going to go boiling point. Okay, and for xenon, the boiling point I want to get, okay, so we're doing boiling points, and I'm looking for xenon, and the boiling point's 165 Kelvin. Why is that significant? Well, my friends in chemistry, okay, if I know that 273 is the temperature I'm comparing it to, think with me for a second. If it boiled at 165, that means this liquid of xenon boils before it gets to 273. Which means at 273, it's a gas. Everything that has a boiling point below 273, guess what? You guessed it, has already boiled. It's a gas. So you know, you also have melting points. Okay? So it melts at 161, so it goes from a solid to a liquid at 161, and then it what? Vaporizes at 165. Let's look at iodine. It melts at 387. Wait a minute. It melts after 273. So we should know iodine is a solid, right? So we can determine solid liquids and gases by their melting point. Think with me something. It doesn't become a liquid in the case of iodine, right? I'm talking about iodine here just to teach you. In the case of iodine, it doesn't melt until it reaches 387. If they say at 273, and they will, 273 is below 387. It hasn't melted yet. It's a solid. So any melting point above 273 means that these things exist as solids. Okay? If we were to scroll through the melting points, we can find a couple of liquids. Okay, not too many of them. All right. For instance, they love to ask about bromide. Okay, so let's go find atomic number 35. Br, that's a liquid at STP. Some people make you memorize this, but you don't. Look, it melts at 266. That means that's before it gets to 273. So at STP, bromide's a liquid. It boils at 332, so we can clearly see we're in the middle phase for a liquid. Okay, so you can determine solid liquids and gases from this table. Okay, back to the problem. So number 40, we're looking for a gas. Remember, gases fill their container completely. And we're looking for a monoatomic gas that doesn't bond with anything, so that's why 40 is choice 1. On to 41. Number 41, based on table G, which compound is less soluble in water as the temperature increases from 0 to 100. Okay, less soluble means that there's less amount of the solute or the substance you're trying to dissolve. Okay, what that means is being less soluble means that the water has a harder time dissolving them. That means the substance you're dissolving doesn't dissolve or escapes as a precipitate or a gas. Okay, so we should know that as water increases from 0 to 100 in table G, and I'm going to draw it here a little bit, most of our solubility curves go up. As we're going to see, if you look, most of the solutes are solids. When you try to dissolve a solid in water, the solubility increases with temperature, right? So the y-axis is the grams of the amount of the substance you're trying to dissolve. So as temperature goes up, these lines go up, which means the solubility increases. But there's a few of them that drop downward. And that's what they're after in this question. And you should know the ones that drop downward are gases. Okay? And the ones that go up are solids. They love to ask that, even in a part 2. And that's the things that I always try to emphasize to my students is the questions that we're going over in the multiple choice are not inclusive just to the multiple choice. They can be asked in a part 2 of another test. They can ask you, what's the solubility difference of a solid and a gas? And gases are less soluble. Gases have tremendous kinetic energy, or they have weak attractive forces. So they don't like to be in a liquid. So with their less attractive forces or their high kinetic energy, if you give them heat, they're going to escape. Think about CO2 or a carbonated beverage on a hot day. It's going to go flat faster than on a cold day if it's open, right? So in any case, all we need to do is find which one of these guys are going down. That's all it is, okay? So potassium nitrate, potassium chloride, ammonium chloride, and ammonia. Let's go to table G. Okay, so table G, otherwise called table Grotsky, they just didn't have the money for the printing. But in any case, we're looking, okay, for the one that was going down. If you notice, there's 3 of them going down, and my gosh, the one choice that we have going down that we had is NH3. I'm not a good tracer, but we can see here in all of its glory, NH3 was the choice. We had potassium chlorate that's going up. We had ammonium chloride that was going up, and I think we had sodium nitrate as the other one that was going up. So the only one going down, okay, was the gas. Notice there's 2 other gases. We have sulfur dioxide and we have hydrochloric acid. Those are 3 gases, all right, and the rest are solids. By the way, something else you should be aware of. Gases are more soluble at higher pressure. Remember, pressure affects the solubility, because if you take a gas, okay, over a liquid, if you have a higher pressure, you can force that gas into the liquid. Okay, so you know this because when you open up a soda bottle, you see the bubbles of CO2 rise when you lower the pressure. Higher pressure, lower temperature makes gases more soluble. More of the substance can be dissolved. But in this case, they were looking for the one that was going down, and NH3 is the one going down. That's the gas. So choice 2. In my explanation, I did explain potassium nitrate, sodium nitrate, but potassium nitrate also went up. It's a solid, so it doesn't change anything. My short-term memory is gone at this height. So number 2 is the answer. It's the only one that is a gas, or the only one going down. You don't have to know it's a gas, but you definitely have to know the one's going down. So 41 is choice 2. On to 42. Number 42. How many moles of Ki needed to make a 0.5 liter of a 0.2 big M aqueous solution? What the heck is M? M is molarity. We've seen it for a couple of different equations. So if you're not knowing what you have to do here, they're looking for a concentration. How much of something we're trying to dissolve, which in this case is Ki, exists in a certain amount of solution? That's a concentration. Now, if you're not aware of that, go find big M. If you're trying to find an equation because you don't know, go to table what? T. Table T is all your equations. We're going to go there now. It's going to be crazy. And there it is, molarity. Concentration. They really should put a big M next to it. Okay, if you notice, they got titration formula that also uses big M, and that's molarity too, so it kind of does tell you that. I also said this was going to be crazy, right? Well, it's not really, but you kind of knew that. But in any case, look at the formula. So big M, or molarity, is the moles of what you're trying to dissolve over the liter of solution. So if I'm not mistaken, they gave you the molarity, they gave you the liters. You're just going to solve for X, the unknown. It's just a plug and chug. So going to table T to find out what formula you needed, if you forgot, is right there. No reason to get this wrong. Let's move back to the test. Okay, so using my formula that I got from table T here, I'm going to just plug it in. I have to be in liters, and it's already in liters here, so I'm just going to plug in 0.5 liters. And the molarity is 0.2. Remember, big M. Solve for your X. If your math is weak, no big deal. This 0.2 is over 1, and cross multiply your hearts away. So 1 times X, hey, that's going to give you X. And then you're going to multiply 0.2 times 0.50. Again, don't do the math in your head. You got a calculator. They should be giving you one for the test if you don't have one. 0.2 times 0.50, and you're going to get 0.1. Okay? And if you notice, 0.10, choice 1 is your answer. Straightforward plug and chug. You had to do a little bit of algebra, but I think you can handle that. So 42 is 1 with the help of table T. Let's do it, people. On to number 43. Number 43, a solution is prepared by using 0.98 grams of sodium hydrogen carbonate. Who cares what that is, but that's not water, so that's what you're dissolving, so that's your solute, in enough water to make that many grams of total solution. What is the concentration of the solution in parts per million? Boy, they're looking for a concentration term. I don't see big M. It sounds like I got to calculate something because this number is nowhere near those numbers. Guess what? Table T is your friend. Let's go see if we can find a parts per million concentration formula in table T. Let's go there. It might be crazy. Oh, and it's crazy. So look at concentration. We dealt with molarity in the previous part, but here's part per million, my friends. It's given to you. Parts per million is equal to the mass of the solute you're dissolving, total mass of the solution, but here we're timesing it by 1,000,000. So there's the formula. Let's just plug and chug, people. Let's do it. Let's go back to the test. All right, so I got the mass of the solute with the total mass of the solution. So they gave me 9.80 grams of the substance I'm dissolving. So I'm just going to get rid of this and add that there. Again, I'm just plugging and chugging what they gave me. So they gave me 9.80. They gave me the total mass of my solution to be 1,500 grams. That goes on the bottom. So let's put it there. So let's get rid of this, and let's put in that value right in the equation that we got from table T. Okay, so 1,500 grams. And boy, we're done. So I'm going to take my calculator. I'm putting 9.80. I'm going to divide by 1,500. I get 0.0065333. Then I'm going to times that. Now, if you're not 10 to the 6, by the way, it's just a way to write a million. Million has 6 zeros. So if you have a calculator you know how to use, I'm going to times that by 1, and I'm going to put 1, 2, 3, 4, 5, 6 zeros, right? That's a million. So I times this answer here by 1 and 6 zeros, or a million, and I get, all right, 6533.3. It's a repeating number. Okay, now, so the only thing that has 6, 5, and 3's in it is choice 2 and choice 4. Now, this is a big number. It's 6,533. Exponents are small numbers. So if you notice, this number 2 would really be, move this decimal place, be 0.00653. Because I've got a number greater than 1, not less than 1, I've got exponents that are bigger. So a little bit of mathematics here. So this actual number, if you move this decimal place 3 places is basically what I have here. They rounded. So this rounded is 6530. Okay, and you say, why did they round? Well, they had 3 significant figures. Okay, this one had 4, so you round to the least number of sig figs. Who cares? So that's what that was about. Okay, just understanding that it's a number greater than 1, not less than 1, and the only number there with 653 is that. So there's a little extra math involved, understanding a scientific notation with positive exponents is greater than 1. This is definitely greater than 1. Negative exponents are less than 1. Our number isn't less than 1. So therefore, number 43 is choice 4. A plug and chug with a little bit of interpretation of the scientific notation. Okay, I think we can handle that. All right, good review there. Number 44. Number 44. A potential energy diagram for a chemical reaction is given below. Each interval on the potential energy axis represents 100 kilojoules of potential energy. So the question reads, what can be concluded from the diagram? Well, the first thing that I do when I look at a potential energy diagram, I essentially look and see where I start and where I finish. It should be clear that we're starting low, we have low potential energy, and we're ending up higher. And when you look in the beginning and the end, and again for those advanced, this is a state function, the difference of where you start and the difference of where you end, okay, is going to be that heat of reaction, the delta H or the enthalpy. All those are synonyms. So it's the change in heat. So we're climbing up this ladder. In fact, we're going up. So the change in heat is going to be positive, right? We have a lot more at the end, and remember these are what? Products. And over here, these are the reactants. So you should understand that when the products have more potential energy than the reactants, the only way we can understand that is that energy must have come into the system. And we are absorbing heat, and therefore that change in heat is going up, as you can see by my arrow. So the delta H is positive. All of this screams an endothermic reaction. Endothermic reactions absorb energy or consume energy in their reactant. So if the reactant is A plus B going to, let's say, AB, let's make it a synthesis reaction, we would have to add the heat into the reactant side because energy is being absorbed because we're going up in energy. Okay, and clearly, as the question states, every single what? Change or integer here, or I guess graduation, is 100 kilojoules. So this would be 200, this would be 300, and so you can see that we're starting with 100 kilojoules, and the potential energy of the products is 300, and the potential energy of the reactants is 100. So obviously we went up 200. So delta H is equal to a positive 200. Don't forget that delta H has a what? Has a definition, and delta H is the potential energy of the products, hey, in this case 300, minus the potential energy of the reactants, in this case 100, and that gives you positive 200. All right, so don't forget all of that. So back to the question and back to what would be the right answer is what can be concluded from the diagram? Well, it is clearly endothermic because energy is going up. The products have more potential energy. The only way that happens is if you're gaining energy, kind of like photosynthesis. Okay, we're making from water and low energy compounds, CO2, we're making a product that has a lot of energy that's used by other organisms, right? Sugar. So in any case, the reaction is endothermic, and the heat of reaction, the delta H, the difference where you start and finish, is a positive. Okay, now something else to think about as an aside is that delta H for exothermic reactions, this would be going in reverse in this case, would be negative because you'd be going down. And if you forget the sign of delta H in table I on the bottom, they tell you that a negative sign is indicative for a delta H for exothermic. So all of those things could be helpful. But it just makes sense. You're going up in energy, so you're absorbing, you're taking energy in. And everyone thinks, oh, what's the potential energy? Well, this is a potential energy curve. Everything's a potential energy. Okay, even the delta H is a change in potential energy. And of course, it all surrounds around the chemical bonds of the reactants and products. The products have more unstable bonds than the reactants, so energy needed to be absorbed. In any case, so choice 2 here is your answer for number 44. Okay, so on 44, number 2. On to number 45. Number 45. Given the formula, this is a structural formula. You don't say that, but you need to know that. Structural formulas help us understand how these molecules exist in space. Even though it's really 3 dimensions, we're seeing 2 dimensions, but it shows us the bonding. A molecular formula, okay, would give us exactly how many carbons and hydrogens, in this case bromides. Okay, so in any case, looking at this structure, it's important. What would be the chemical name? Well, the organic chemistry is centered around the carbon, of course. Everything that has carbon is an organic molecule. And we know that structure is king. I always say this. Structure is king because if you change the structure, you change the property. So that's why we have a chemical name that describes exactly the structure, because if you have a different structure, it will have a unique set of properties, even though you're not changing, okay, the amount of carbons, hydrogens, and bromides. Any case, how do we name? Longest continuous carbon chain. Pretty simple here. We have 1, 2, 3, 4, and 5. If you go to table P, that would be, okay, a pent. And because there's single bonds between the carbons, and table Q, that tells us that's an ane. Now we have 2 attaching groups, or we have 1 type attaching to 2 different carbons, and these are halocarbons. If you go to table R, they show you how to name this. Okay, so this is called a bromo. So table R reminds us that a B is called a bromo. They also show us that a Cl is a chloro, and an F is a fluoro, and an I is an iodo. But in any case, table R is your friend here. So we have bromides on the 1st and 2nd carbon, okay, or it could be on the 4th and 5th. Well, it's going to be on the 1st and 2nd carbon. And you say, well, why do we do that? Well, that's just the IUPAC naming system. They decided that the things that add to the carbon chain, we have the carbon chain named here, things that add to it are called substituents, and they always are put on the lowest carbon. That's just a convention. A convention is something they decided on. So we always go to lowest number. So that would be 1, 2. And the reason I do 1, 2 is because I need to show the person this structure where the bromides are located, and there's 2 of them. And so I use di, and I write bromo to tell us there are bromides on a pentane, and there's 2 of them, and they're located at each of these carbons. Some people give 1 number when they're doing this, when they learn is, hey, it's a dibromo, I only need 1 number. And I always say, well, draw the compound. Where does the 2nd bromide go? So you should be able to draw this with the naming structure. So this naming system is one which you can actually draw, and it's important that you're able to do that. So if you were given 1, 2 dibromo pentane, which by the way, of course, is choice 3, could we draw this? So I tell my students, always start with the carbon chain. So pent, 1, 2, 3, 4, and 5. And if you don't know the prefix that tells you the number of carbons, table P. I don't think I need to show you that. All right, now in table Q, if these things have single bonds, they'd be ending in ane, and table Q gives you that information. Now we have on the 1st and 2nd. So 1st and 2nd carbon, I'm going to add bromides. Now I could have added them here because I can pick it up and flip it over, okay? But it's the same idea, all right? So and then I have to get everything right, fill in the rest of the carbon. Carbon must make 4 bonds because it has 4 valence electrons. It needs 4 more to be shared to fill its octet. You fill in the rest with H's. You don't have to fill in the H's that dashes work. So you can see how this naming system, you can actually write the structure, and the structure provides the name. Okay, so in any case, 45 is choice 3. Notice there's a choice there with the same name except 4 to 5. And remember, you always go with the lowest number for the adding groups. Okay, so 45 is choice 3. And on to number 46. Number 46, the diagram and equation below represent an electrochemical cell. Now, electrochemical cell could either mean the battery. That's a spontaneous process. Spontaneous means it works without an input of energy. A battery works by itself. It also could be called a voltaic cell. It's another word for it. And then you can also have one that needs a battery, which is electrolysis or electroplating. And I guess I kind of gave it away, didn't I? So this has a battery. So it needs an input of energy to force the chemical reaction to go. This chemical reaction does not go unless we force it to happen with the battery. It's non-spontaneous, but it's not chromatography, which is, by the way, that's separating a mixture based upon solubility. It's not distillation. That's how we separate a mixture based upon boiling points. It's not polymerization. We're not making a monomer repeat over and over again, like think about amino acids bonding together to make proteins. It's electrolysis. Boy, I don't know. It's a pretty simple one there. If you got it wrong, I'm sorry, but you recognize the fact that it has a battery. Okay, the choices weren't very good, but again, if you didn't understand, if you see the battery, therefore it requires a battery. And look at the word electrolysis. It's got the word electricity in it. It needs electricity. It's non-spontaneous. I'm teaching you the other parts to this. Okay, all right. So number 46 is 3 by process of elimination, or the idea that, hey, you needed electricity, right? The batteries provide electricity or energy to make this happen. All right. And by the way, this would be like an endothermic reaction as well. And again, I'm teaching you all the other types of concepts that can go with this. You may not see this exact same question, but you should recognize the fact all the things that I'm teaching are connected to it. All right, on to number 47. Number 47, which aqueous solution has the greatest ability to conduct an electrical current? So what they're talking about here is, who is the best electrolyte, right? An electrolyte. An electrolyte is an aqueous solution that has what? Free ions. Ions that are free from their crystal lattice positions can move, and when they move, they can create, okay, or conduct a charge, okay? So who are electrolytes? You need to know the electrolytes are acids, because what do acids do? They break apart into H pluses or H3O pluses, which, my friends, are free ions. You've got to get that. We have bases. What do bases break apart into? Bases break apart into hydroxides, more free ions. And what about a salt? Don't forget that a salt is something called an ionic. Well, if it's NaCl solid, it's going to break apart into its what? Free ions. So you got to understand that we're talking about things that break into free ions. So if you look at your choices, who's an acid, base, or a salt? Choice 1 and 2. NaCl is a salt. Now you say, Mr. Grotzky, how do I know that this is not an acid or a base? Well, if you look at table K for your acids, acids have an H in front to scream that they give off an H. And bases in table L usually have written for as a hydroxide ion bonded to a metal here. This is a non-electrolyte. Sugar will not conduct a charge. Maybe you've seen that demonstration in class. Your teacher put sugar in water and tried to see if the light bulb lit, and it will not, because it does not produce free ions to conduct charge. Positives would run to one, and the negatives run to the other. And by the movement of ions, you can conduct charge. Sugar doesn't break apart into ions. It is a non-electrolyte. It's a molecular compound. It doesn't fall under these three things you need to know that electrolytes. Now the question states, who has the greatest ability? Since we've narrowed down our choices to 1 and 2, these are both solutions of free ions because it's a salt dissociating into its free ions. But who has the greatest amount of ions? Well, molarity is a concentration unit. Who's got the greatest concentration of ions? The higher molarity. Remember, molarity from table T, if you've been with me through that entire test, molarity, of course, is equal to moles of what you're trying to dissolve over a liter. So if you've got a greater molarity, you've got a greater amount of substance, in this case, a greater amount of free ions. So choice 1 is your answer, the greatest amount of free ions. And of course, as I keep saying, in the free response section of the test, they could ask for what makes an electrolyte, and you say free ions. These concepts are repeatable in different ways in different parts of the test. Okay, so 47 is 1, on to 48. Number 48, what fraction of the original sample of iodine-131 remains unchanged after 24.068 days? Okay, so you should recognize that if I'm looking for what's remaining after a certain amount of time, this is a half-life problem. You need to recognize, and also recognize where you are, okay, in the test. Okay, nuclear chemistry is toward the end of the 1 through 30 sprint part of your test, and then it's also toward the end of the 31 through 50 part of your multiple choice. These things tend to go in order. So this is a classic half-life. So when I do half-life problems, I tell my students to write a 0 line. 0 time, 0 half-lives, and 100% of my sample, which I'll put 1 over 1, but you could put the original sample there. Now they said the total time was 24.063 days. Now I will tell you that the amount of halvings that occur half-lives will always be whole numbers, but if you don't trust me, we have that time. What we need to know is the half-life of iodine-131. If I know the total time is 24, I need to know how many halvings have occurred in that time period. And that's what a half-life is. It's the amount of time it takes for half of the unstable nucleus to become stable and to decay and change itself, transmutate into something more stable. So I need to go to table N, which I call hey, goodbye, because it's the last table I teach. So let's go to table N. So here at table N, we find iodine-131. We see that half-life is 8.021 days. So they gave us approximately, this is approximately 8. They gave us approximately 24. Hey, 24 divided by 8. If you want to do the math, it's going to round really, really close to 3 halvings have occurred. If each half-life is approximately 8 days and the total time is 24 days, you could see that there was 8.021 days, or 3 halvings. Okay, so I needed that piece of information. Let's go back to the test. Okay, with that in mind, okay, there was 3 halvings. So the first half-life, we'll do 1, 2, 3 half-lives. And again, if each half-life was 8 days and 24 days, and again, I am rounding because they're gonna do whole number type of events here for half-lives. So 24 divided by 8 is 3 halvings. So I do 3 half-lives. And let's half 1 over, what's half of 1? Well, 1/2. Okay, what's the second half-life? What's half of a half? Oh, that's 1/4. In the third half-life, or third halving, what's a half of a 1/4? 1/8. And my friends in chemistry, that's your answer. Okay, so choice 1 is 1/8. You have to recognize you're in a half-life problem. I really think the table does help. I've seen, again, the 0 timeline kind of keeps you organized, but you needed table N for the half-life in this instant. All right, so I don't think that's one you can definitely do. Please recognize, oh, that's a half-life problem. Okay, how many halvings have occurred? All right, on to 49. Number 49, given the equation represented in a reaction. Okay, well, this is a nuclear reaction. We should recognize that. Why is it not a regular reaction? Because we're seeing how the nucleus is changing, not how the chemical formulas using chemical bonds are changing, okay, in a chemical reaction, or how the phase is changing in a physical reaction. So combustion and substitution, combustion usually represent is like, hey, we have, methane, CH4, plus oxygen, and it's going to give us CO2 and water. I'm not balancing here for speed purposes, but these are chemical reactions. The top third of table I, it's not a nuclear. Substitution is when I have an unsaturated hydrocarbon like ethane, and I'm going to add chlorine to it, and it's be Cl2. And of course, we're going to have to substitute an H for chlorine, and we're going to make one of these is going to be chlorine. And of course, we're going to make HCl because there's no room. But that's a chemical reaction. We're showing how the bonds are being rearranged and broken. We don't have chemical bonds. So we're talking about a nuclear reaction. And which one is it? Well, this is nuclear fusion. We're fusing light nuclei together into a little bit heavier with tremendous amount of energy and mass loss, by the way. A little bit of mass is lost and equals to a lot of energy. Nuclear reactions have more. What's the difference of fission? Well, fission is when you have a large nucleus, right? Like a uranium-92. I'll make this 235. With a slow-moving neutron, it is artificial, just like this one is, because you need to have two things colliding. With a small, in this case, neutron, you're going to split into maybe a barium and a krypton, and then, 3 more neutrons. Key here is the barium and the krypton are way below atomic number 83. Those are stable nuclei. When you have more than 83 protons, it makes the nucleus very unstable. Little tiny protons in a very small place, the atomic nucleus that Ernest Rutherford discovered in the gold foil experiment, shows us that if we stuff that small area with a lot of protons, that nucleus has a tough time staying that way. So some of these guys can be split. So fission is splitting a big nucleus into smaller nuclei. Nuclear fusion, like the word states, fusing, we're taking light nuclei, putting them together and making a little bit of a heavier one. You have to be able to recognize it. So choice 1 is not the answer. Choice 2 is the answer, nuclear fusion. And you should also know nuclear fusion, compared to fission, gives off more energy, is safer in the sense that it doesn't give off greenhouse gases, it doesn't pollute the environment with radioactive wastes. There's no potential for a meltdown in a nuclear reactor that uses fission. But the problem with fusion is we haven't figured out how quite to do it yet. Okay, so 49 is 2. On to the last multiple choice question of this test. On to 50. Number 50. Last question of the multiple choice section. And know where you are in the test. If you're toward the bottom of the 31 through 50, in this case around 50, 47, you're usually in a nuclear chemistry area. They tend to go in order from unit 1 to 10. And if you're in the close to 30 in the 1 through 30 range, same idea. So this can be helpful. But in any case, I'm looking at this reaction here. And it says, given the nuclear equation, hey, it's a nuclear equation because, hey, chemicals are not being bonded and rearranged in different formulas. We're showing how the nucleus or nuclei are changing when these guys slam together, okay, to give off energy. And this would be an example of a fusion reaction, okay? So here comes the question. What is the amount of mass converted to energy? Now, this may seem strange to you, but in a nuclear reaction, all nuclear reactions, whether it's radioactive decay, beta, alpha, okay, there's a little bit of mass that's converted to energy, and that energy is tremendous, okay? And of course, the energy given off in nuclear reactions is greater. But in this question, what is the amount of mass converted to energy as a result of the reaction? So they want to know, really, how much is missing? They call this mass defect, and you need to know this, okay? Maybe not for this particular problem, because you're just asking for the math here, but mass defect just means that there's missing mass. The mass missing equals the energy. So nuclear reactions that give off more energy than others have more mass missing, more mass converted. But in any case, let's go find this. So what I'm going to do here is I'm going to add up the reactant's atomic masses or isotopic masses. So I take 6.0151 and then I'm going to add that to 2.0140, add that together, and I get 8.0291, and it should equal, if there was no missing mass, the mass of my products. But notice there's 2 of these helium nuclei, so I do 2 times this number, which they're showing you that. They're showing the parentheses, so they're kind of giving that away. 2 times 4.0026, and I get 8.0052. Now, they're giving you a distractor. Because the last number that you calculate is right here, a lot of people say, oh, that must be the answer. No, 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 no. What's the missing mass? These numbers should be equal if this was a chemical reaction, because it's a nuclear reaction. Some of the mass is missing and converted to energy. So how much is missing? Subtract those 2 numbers, right? So subtract those 2 numbers in your calculator. So 8.0291 minus 8.0052. So put that in your calculator of fun, because calculators can be fun. And I'm doing that right now, 291. And what I get is, the missing mass is 0.0239. And of course, exactly what's written here. So really nasty distractor here by just having this number here, which is 2 times that. But you had to see what was the what. How much mass was converted to energy? What was really the missing mass? Okay, so that's what that was about. Choice 1 is your answer, 50. And although I haven't seen quite a problem quite like this before, it's definitely doable, as long as you understand that in nuclear equations there's mass missing. Okay, so 50 is number 1, and if you want to continue to my other video that will be posted soon, that's the free response section. So if this helped your multiple choice studying, good luck, have fun, and good luck with the test.